On August 15th, 1977, a strange signal from the constellation Sagittarius was received by the Big Ear radio telescope. The signal, known as the WA signal, reached an intensity up to 30 times higher than the usual signals and had a duration of 72 seconds. Its name comes from the note written at that moment by the person who discovered it, Jerry R. Eman, collaborator and SETI project, a project for the search for extraterrestrial intelligence founded by NASA in 1960. The WA signal is, among all the strange signals received up to now, the one that has the greatest likelihood of having been emitted by intelligent extraterrestrial beings, despite its origin still being uncertain to this day. In a vast universe, 40 billion years old and containing 500 billion galaxies, science is convinced that there must exist, or must have existed, extraterrestrial intelligence. In this vastness, it would seem that there should be fullness of life out there. With this conviction, human beings have searched for it and still search for it incessantly. State-of-the-art radio telescopes track the sky day and night, year after year, in search of any sign of extraterrestrial intelligent life. Nevertheless, in 2009, everything changed. That year, NASA launched the Kepler satellite into space. And thanks to it, we have found thousands of Earth-like planets where conditions for life might be possible. This has meant, undoubtedly, a total revolution in the search for extraterrestrial intelligent life. Given the important advances in astrophysics, some scientists believe that there is a chance of finding extraterrestrial intelligence in the next decades. Seth Shostak, astronomer and director of SETI, Search for Extraterrestrial Intelligence, declared before the House Science Committee of the American Congress that in a couple of decades, we will have found evidence of its existence.
The chances of finding it, I think, are good, and if that happens, it'll happen in the next 20 years, depending on the financing.
A first contact could be close. The question is, do we really want them to find us? What will these forms of life be like? What will their aims be? Is anybody out there? Given the millions of billions of Earth-like planets, life elsewhere in the universe, without a doubt, does exist. In the vastness of the universe, we are not alone. Albert Einstein. 4.5 billion years ago, in the vastness of the universe, the Earth, our home, was formed. From the birth of the universe, it took 14 billion years for human beings to arise, just 6 million years ago. To give us an idea of the time which has passed until our first steps, Carl Sagan made a time comparison in which, if the age of the universe was a year, the Big Bang would have occurred on January 1st. On September 8th, the Sun would have formed. On September 11th, the Earth would have formed, and we would have been born the last day of the year, December 31st, at 11:39. How many things must have happened in other places during the same time?
Today, when we take a look at what we know about the universe, and what we know about the origins of life on this planet, it leads us to think that the same things that happened here might well have happened elsewhere. And so life beyond this planet is quite plausible in terms of the science that we know today.
We see the organic building blocks that are essential to life on Earth. And so the raw stuff that's necessary for life is out there. The places that life could live is out there. The big question is, do they come together and form a second Genesis?
We take up a tiny place in the immensity of the universe. The Milky Way, the galaxy we live in, might have around 100 billion stars, among them our sun. In total, it measures around 100,000 light years in diameter.
Maybe there are a million, maybe there are a billion, maybe there are 100 billion planets in the Milky Way galaxy that could support life, the kind of planets that earthly life could survive on. How many of them have cooked up their own life?
Here, from one end of the Milky Way, we, an intelligent civilization, wonder if it's possible that we are alone in all of this vastness.
There's just a lot of real estate, a lot of room for life in space. We've now learned that planets are as common as cheap hotels. They're all over the place. There are 1 trillion, that's 1 million planets just in our own galaxy. If there is no life on any of them, then Earth is a miracle. A miracle. And I'll tell you this, for scientists, believing in miracles is usually not a good strategy.
When we think about how vast the universe is, it would be incredible if there's no other life out there. There are hundreds of billions of stars in our galaxy alone, and there are billions of galaxies in the universe. If life appears on only a minuscule fraction of those planets, then life is prevalent throughout the universe.
That's why human beings, in their enthusiasm for knowledge and exploration, have started the search for intelligent life, with the hope of, sooner or later, finding it, or being found by it.
Oiknis poteste chairete, airenikos pros philos elelithamen philoi.
Paz e felicidade a todos. تحياتنا للأصدقاء في النجوم يا ليت يجمعنا الزمان.
Բոլոր անոնց, որ գտնվին եզերքի միքամազություններեն անտին, ողջույններ.
पृथ्वी ઉપર વસનાર એક માનવ તરફથી બ્રહ્માંડના અન્ય અવકાશમાં વસનારાઓને હાર્દિક અભિનંદન. આ સંદેશો મળે વળતો સંદેશો મોકલાવશો.
This search can be done in two ways: tracking signals that may come from any extraterrestrial civilization, or sending our own messages into space, which may be received by one of those civilizations someday.
Active SETI, also sometimes called METI, messaging extraterrestrial intelligence, reverses the roles. Instead of passively listening for a signal from another civilization, we send intentional, powerful signals to nearby stars in the hope of getting a reply back.
With this goal, in 1977, the most elaborate and comprehensive message to date, The Sounds of the Earth, was launched into space. A moving introductory message including everything that human beings considered that an extraterrestrial civilization should know about our species. It was included on a golden record on each of the Voyager interstellar space probes, launched that same year from Cape Canaveral.
It was a golden record. On one side, there were encoded music from around the world, greetings in 55 languages, a 12-minute sound montage of the evolution of life on Earth. And on the other side, there were pictures, over 100 pictures describing some basic mathematical principles and the diversity of life and culture on Earth.
The content of the recording was carefully chosen by NASA and a committee chaired by astronomer and author Carl Sagan. The audio section has a salutation in English from the UN General Secretary and short messages in 55 languages, welcoming and wishing peace to all forms of life.
Witajcie, istoty z zaświatów.
Hello from the children of planet Earth.
But that one was not the only message sent.
There have been a few symbolic transmissions to other worlds. The most famous transmission to another civilization happened in 1974 from the world's most powerful radio telescope in Arecibo, Puerto Rico. It was a very simple message. It took 3 minutes to send, and it provides a mathematical and scientific overview of life on Earth.
Nevertheless, the search for extraterrestrial life is not founded just on the sending of messages in the hope of a response someday, but on the development of a search for signals that may indicate the existence of that intelligent life.
SETI, as a scientific exploration, actually got its start within NASA in the life sciences portion of NASA. People were interested in the question of life beyond the Earth, and this program developed within NASA. It launched actually in 1992. It was called the High Resolution Microwave Survey. In 1993, Senator Bryan from Nevada terminated NASA's funding for SETI, and he terminated with a vengeance so that NASA was unable to recover and come back the next year with another SETI program. So at that point, because we had already formed a nonprofit institute called the SETI Institute to help NASA stretch its funds as it did this SETI work, in 1993 we said, okay, we've got a nonprofit, we're just going to go out and raise money to do this privately.
The SETI Institute is nowadays the main world institution devoted to the search for extraterrestrial intelligence.
It's a project called SETI, the Search for Extraterrestrial Intelligence.
This search is based on the use of radio telescopes. Radio telescopes receive radio waves. As we can't go to space aboard spacecrafts to find that intelligent life, what we look for are radio signals.
What we're looking for is a signal that's at one spot on the radio dial. Just like when you're listening to the radio in your car. You know, you tune across the dial, you hear static everywhere, and then at one spot you're near, and there's a station. Okay? That's the signal that's produced by a transmitter somewhere. It's not natural static. It's not like a quasar or a pulsar or galaxies or hot gas, cold gas. All those things in space make radio noise, but it's all over the dial. So we look for signals that are at one spot on the dial, and of course the source of the signal has to be up in the sky. Those are the kinds of criteria we use to know that even if we don't know what it means, we at least know they're there. They're on the air.
One of the biggest SETI projects, started in 2007, is the Allen Telescope Array, which seeks to install 350 antennas to receive possible messages from outer space.
We designed this. We went to Paul Allen and asked him to fund it, and he was generous to fund the first phase of construction of what we now call the Allen Telescope Array. It's in Northern California near Mount Lassen. The Allen Telescope Array has 42 telescopes. Someday we hope to grow it to 350.
The Allen Project will become the most powerful instrument in the search for signals from other civilizations in our galaxy. Since it was launched, after just a few months in operation, it has been able to analyze the same amount of area of the universe as in the last 45 years of SETI's existence. Another of SETI's most famous innovative projects is SETI at Home. It was started in 1999 by astronomers at the University of California in Berkeley, and it uses an army of millions of amateur internet users. From home, anyone can be part of this enthralling pursuit. The screensaver analyzes some of the data that comes from the Arecibo radio telescope in Puerto Rico. Up to now, more than 5 million people from all over the world have participated and are processing all of the info captured by the Arecibo radio telescope. The SETI at Home project has grown so quickly that it is the biggest ever of its kind. Both projects, Allen Telescope Array and SETI at Home, have been a huge advance in the search for intelligent life, giving hope for discoveries in the near future. But undoubtedly, what has radically revolutionized and pushed the search for extraterrestrial intelligent life is the Kepler mission, which is focused on the search for potentially inhabitable planets. It was launched by NASA on March 6, 2009, and orbits the Sun looking for extrasolar Earth-like planets where life may be possible.
Kepler, which is a space-based telescope that was launched about 5 years ago, is on the hunt for planets. Kepler has found literally thousands of planets or planetary candidates. It's a planet-finding machine.
The Kepler spacecraft has been a game changer in the search for other intelligence. Kepler now can tell us which stars have planets around them and which of those stars are Earth-like. That means we now know where we can point our telescopes to look for a twin of Earth.
In 2011, for the first time ever, Kepler provided scientists with a census of the Milky Way. For the first time ever, we can calculate how many stars in the Milky Way could have a planet like ours. Around 1 billion.
So one of the big triumphs of astronomy in the last 2 decades is to show the majority of stars have planets. There are planets all over the place. There are more planets than stars.
According to the data, in the near future, millions of inhabitable planets may be found just in our galaxy.
What Kepler has shown is that maybe 1 in 5 stars has a planet which could have liquid oceans, a bit of an atmosphere. In other words, the kind of place where you might want to build yourself a house, right? So 1 in 5 means that just in our galaxy, there are tens of thousands of millions of cousins of the Earth. That's a lot of real estate.
This data is crucial to answering the question of whether we are alone in the universe and helping us to resolve some unknowns of one of the most famous equations in astrophysics, the Drake equation, which is now of major interest.
The Drake equation is a way to grapple with all of the issues most central to determining how many civilizations are there out there in our galaxy trying to make contact. The Drake equation looks at 7 independent factors and tries to put a number on each of them.
So you multiply all those up, and you come up with a number that we call N, the number of potentially communicative civilizations in the Milky Way. Our star is the rate at which stars have been born in the Milky Way galaxy over the last few billion years. So it's a number that is stars per year. Our galaxy is 10 billion years old, and early in its history, stars formed at a different rate. All of the F factors are fractions. Each one must be less than or equal to 1. F sub p is the fraction of stars that have planets. N sub e is the average number of habitable planets in any planetary system. F sub L is the fraction of planets on which life actually begins, and F sub I is the fraction of all those life forms that develop intelligence. F sub C is the fraction of intelligent life that develops a civilization that decides to use some sort of transmitting technology. And finally, L, the longevity factor. On average, how many years do those transmitters continue to operate?
That is perhaps the most elusive term of the Drake equation. As we look into our own future, we wonder, will we survive as a technologically adolescent civilization? Will we last long enough to make contact? That is the big unknown.
The Drake equation includes a series of terms whose value we can't know exactly.
It's just a fantastic framework with which we can organize our ignorance, because you can't solve the equation. There are no right answers to that equation, not yet.
As we shift into the more biological and cultural terms of the Drake equation, we move into areas where we're uncertain.
But during the last few years, we've seen how exoplanets have arisen in front of our eyes, thanks mainly to the Kepler space satellite.
When Frank Drake first wrote down the Drake equation back in 1961, he put his own personal estimates into each of those vectors and came up with a number, his estimate, which was 10,000. So within the Milky Way galaxy of 100 billion stars, he thought 10,000 of those stars might host technological civilizations.
What do we know now that we didn't know in 1961? Well, we know one or two of those terms a little bit better. And they kind of agree with the optimistic estimates that were made 50, 60 years ago.
There are other estimates that are extremely pessimistic. There's only one, and it's us. Carl Sagan had a number that was more optimistic. He said probably 1 million was his guess. We think we know that our star and N-sub-E are both numbers that are closer to 10 than, say, to 1. And all the F factors are less than 1. Some of them may be much less than 1. But of all these unknowns, the biggest unknown is L. So perhaps the most useful version of the Drake equation is simply to say that N is approximately equal to L. The information in this equation is very clear. Unless L is large, N will be small.
And these are estimates just for our galaxy. But we don't have estimates just for our galaxy, but for the visible universe. This fact multiplies the chances for the existence of extraterrestrial intelligence. The Hubble Space Telescope has given us an approximate calculation of the total number of galaxies in the viable universe. 100 billion. So we can calculate the number of Earth-like planets in the visible universe. 1 trillion Earth-like planets. The universe is 14 billion years old, so there has been time enough for intelligent empires to arise and possibly fall. It would be miraculous if no other advanced civilization anywhere had ever existed. It's just a matter of time until we find them. Radio telescope technology is becoming more and more advanced, and some scientists believe that the first evidence will be found in the next decades.
So far, we've looked at a little over 10,000 stars very carefully with the Allen Telescope Array. In the next couple of decades, that'll be 1 million stars. And by the time you've looked at 1 million stars, that's a reasonable number to find intelligent life, if it's really out there.
In fact, people like Craig Venter and Daniel Cohen have said 20th century was a century of physics. 21st century is going to be the century of biology. But my colleagues and astrobiologists and young scientists are saying, yes, the century of biology on Earth and beyond. This coming century, this 21st century, could well provide us with evidence of life beyond Earth and a biochemistry that's different from the only one we know.
The chance of an imminent discovery brings with it a controversial question. What will the first contact be like? What could human beings say to another intelligent species? What introductory message can we compose about human beings, that species that inhabits one of the edges of the universe, and who have developed enough to wonder if there is anyone else out there, or to try to find them?
There should be a deliberative process to think about how we want to present ourselves to other worlds.
And that is a dynamic conversation that we're having now in the science community. Should we transmit? If we do, who should speak for Earth? What should they say? In what language? How?
It's not a simple task to ponder a first introduction to an extraterrestrial intelligence, and the even more complicated question of how to compose that message to make it understood.
How we would say something meaningful to another civilization. It is going to be one of the most tremendous intellectual challenges humankind has ever faced.
Composing a message that can be understood by aliens will be extremely difficult, and conversation may be impossible.
In order to make contact with another civilization and truly understand them, we have to find a language that any scientist who is engaged in SETI anywhere in the galaxy will understand.
This is what's called active SETI, or METI, messaging to extraterrestrial intelligence.
If you can build a radio transmitter anywhere in the galaxy, you have to know that 2 + 2 = 4. And so it's basic mathematical principles like that that we use as the foundation for a language to communicate with extraterrestrials.
In terms of the message content, how it should be sent, and what it should say, what would we say about ourselves? And what are efficient encoding schemes, and how do we provide a tutorial so that they can figure out what the scheme is?
My suggestion is to send the internet, right? Send so much information that they can look through it and find pictures, videos, sounds, text, of course, and they'll be able to understand it, sort of like the hieroglyphics.
Several messages have already been sent to space, and we hope to receive an answer someday. The first sent message was attached to the Pioneer 10 space probe, launched by NASA from Cape Canaveral on March 2, 1972. A golden anodized aluminum plate designed by astronomers Carl Sagan and Francis Drake was affixed to the probe. It was a kind of an interstellar message in a bottle. On it, drawings of 2 human figures appear, one feminine and one masculine, with the image of the spacecraft behind them to show the proportion of the human silhouettes. Our address in the universe was also included, as well as a scheme of our solar system. Another similar plate was affixed to the Pioneer 11. The next message, sent in 1974, was designed by the Dr. Frank Drake and transmitted by the Arecibo radio telescope in Puerto Rico. This message is generally known as the Arecibo message.
It was a very simple message. It took 3 minutes to send, and it provides a mathematical and scientific overview of life on Earth. It starts with a description of our numbering system in a binary code, numbers from 1 to 10, and then using those numbers, a description of chemical elements that are essential to life on Earth. And once we can talk about those chemicals, we can talk about the way they combine into molecules, including DNA, the core of our genetic material here on Earth. The Arecibo message also gave a description of our solar system, the population of our Earth, even a diagram of the telescope that was used to transmit the message.
1977 saw the launch of the Sounds of the Earth, the most elaborate and comprehensive message to date. Recorded on golden records, they were affixed to each other on the Voyager spacecrafts. Besides salutations in 55 languages, they included an audio section devoted to the sounds of the Earth. Volcanoes, lightning, wind, laughter, and the message in Latin, per aspera ad astra, through hardship to the stars, in Morse code. Also included were eclectic selections of music from different cultures. The Brandenburg Concerto No. 2 by Bach, the Magic Flute by Mozart, the Melancholy Blues by Louis Armstrong, Beethoven's Fifth Symphony, as well as traditional music from different cultures. In addition to the audio, 116 photographs were sent showing different forms of life on the Earth and human society. Mathematics definitions, the structure of DNA, a diagram of the fertilization and birth, a violin with musical notes, and so on. Will anyone receive these messages? Will we have an answer? But above all, what will those who receive this message be like?
I think that one of the best things about finding life, a second Genesis, life that isn't related to us, somewhere else will be to begin to understand how biology can be different.
I mean, we don't even know if they'd have the similar biochemistry. But on the other hand, we're carbon-based life forms, and carbon, which is all over the universe, of course, is great at hooking up with other atoms to make complex chemistry, and since that's what we are, they might be carbon-based. That's not crazy.
We're having a hard time figuring out what other ways there might be. We're working on it from the bottom up with synthetic biology, trying to build life in other ways. But I think life elsewhere will have evolved to be perfectly suited to its environment. If the environments are similar to ours, then there could, in fact, be a lot of similarities. If the environments are extremely different from those that we enjoy here on this planet, then I think it's unimaginable. I'd love to find out what we can't imagine.
In fact, as we imagine the kind of beings we make contact with, they may not be biological beings at all. On Earth, we are anticipating computers becoming advanced enough that they may even deserve the term intelligence in the next century or so. So if we make contact with a civilization that's thousands or millions of years more advanced than we are, the intelligence on the other end of the line may be an artificial intelligence.
These hypothetical forms of life may have abandoned their biological bodies a long time ago to create a computer body. They may have the ability to build a quantum computer with an extraordinary computing power, a super-intelligent device with the same capacity as a conventional computer that occupies a whole planet. Then they may have lost their consciousness of the self to be absorbed by a global digital network of minds, a great collective consciousness.
But in terms of what they'd be like, what they'd look like, nobody can really say, except this. Probably within 100 years, we're going to develop thinking machines here on Earth. So I think it's very likely that if you actually pick up a signal coming from elsewhere, it's not coming from some sort of biological being, it's coming from a machine.
The search for extraterrestrial intelligence is not really different from the search for our own future. The absolute ignorance about the possible aims of an extraterrestrial intelligence is what has led some scientists to voice their misgivings about announcing our existence to extraterrestrials, at least until we know their intentions toward us.
Active SETI is a controversial topic. No less than the cosmologist Stephen Hawking warned, do not transmit to ET. When he said that in 2010, his concern was that aliens may invade Earth to strip mine our planet, taking our rare resources. Well, Hawking is a genius, but he can't predict the future. And so there's no way he could have told that Earth-like planets are distributed everywhere. But even if there is a danger, even if another civilization can come to Earth, it's too late to conceal our existence. Any civilization with the ability to travel between the stars can already pick up our radio and TV signals that are leaking off into space. There is no added danger of transmitting signals through active SETI.
In any case, considering the data we now know, a first contact may be possible in a short time. It's also possible that some civilization has already listened to our messages. Nevertheless, how is it possible that if there are other civilizations, we haven't yet received any evidence of their existence? This is what is known as the Fermi paradox.
The physicist Enrico Fermi famously asked, where are they? The idea was, if in fact the universe is populated with life, why haven't they come here?
The formulation of that paradox arose when the physicist Enrico Fermi was working on the Manhattan Project, whose aim was the development of the U.S. atomic bomb. Fermi's answer to his paradox was that every advanced civilization develops, along with its technology, the potential to exterminate itself. as was thought to be happening at that time. The fact that other extraterrestrial civilizations had not been found implied for him a tragic end for humanity. However, there are several possible solutions to the Fermi paradox. They do exist, but they are not communicating with us. They do exist and communicate, but we can't hear them. They do exist and have been here, but we weren't. They do exist, but most people don't know it yet. They have disappeared. Maybe these civilizations have already destroyed themselves as a consequence of a nuclear war or some other cause. But we find even more solutions to the paradox.
Well, there are a lot of answers to the Fermi paradox. One is that it's actually very difficult to travel between the stars. Even over the course of long periods of time, it takes a lot of energy, it takes a lot of commitment, and anything that you can gain in terms of information, you could get a lot cheaper simply by sending radio signals.
Another possible solution is that we aren't interesting to them. If some civilization were able to come to the Earth from the stars, it would have to be thousands or millions times more advanced than ours, and we may not have anything interesting to offer them. Such a civilization might consider us as primitive, as we consider a simple beehive. Would it make any sense for us to interact with bees and try to make them understand our advances in spacecraft missions, nuclear energy, or quantum mechanics?
Or maybe there is colonization and we just don't happen to see it because it's not nearby or it isn't very obvious.
Paradoxically, the galaxy could be filled with intelligent forms of life, but we are so primitive that we have not even realized it. Another explanation for the Fermi paradox is that we may have already received those signals, but we haven't realized it. We haven't perceived the signals, or we haven't been able to understand or decode them. In this case, some strange signals from outer space have been received. Their origins are now being investigated, and they have posed serious questions for scientists.
The most famous signal that's been detected came in 1977. It was at Ohio State University's Big Ear radio telescope. And in the course of listening for signals from another civilization, there was this message that was strong, that was spread out over frequency. It looked exactly like the kind of signal we would want to get from ET.
During his work on the night shift on July 15, 1977, Jerry R. Eman, professor of the State University of Ohio and SETI project volunteer, observed the weird transcription of the radio signal made by a computer in a section of paper feed to confirm later that it was the most intense anomalous signal detected up to that point by a radio telescope. The signal of unknown origin had a duration of 72 seconds and reached an intensity 30 times higher than conventional signals, and had come from the constellation of Sagittarius.
In fact, it was so astounding that when the technician was looking at the printout the next morning, he wrote "wow" in the margin, and that's become known as the wow signal.
The computer processed the signals received into a series of alphanumeric characters. It wrote the sequence 6EQUJ5, which has kept the international scientific community on edge until today. Eman and his team studied the signal in detail. In the end, they were able to rule out that it had been part of any interference coming from the Earth. So during the following month, the operators of the radio telescope tried to reposition the signal, but they didn't succeed.
Well, many times in the decades since then, astronomers have looked at the same part of the sky to see whether they can find the wow signal again, but we've never been able to replicate it. So the key to progress in SETI is to be able to find a signal that looks as good as the wow signal, but now to be able to find it not just once, but over and over and over again.
Today, the origin of that signal is still under investigation. Another signal which provoked important debates was the radio source SHGB-02+14A, discovered in March 2003 by SETI at home and announced in New Scientist on September 1st, 2004. Since SETI at home started, more than 5 billion signals have been detected that, because of their mathematical profile or their lack of repetition in time, have been ruled out. Among all of them, the candidate SHGB-02+14A was one of the very few that was confirmed again, and the only one to maintain a high statistical chance of being intelligent and of extraterrestrial origin. Another relevant signal was the one observed by the Australian astronomer Regbur Bathal, a SETI collaborator, who found a strange signal close to what years later would be confirmed by NASA as the first habitable planet, the Gliese 581, just 20 light-years away. On the NASA website, in the section Astrology Picture of the Day, we found an explanation for the signal. No one knows for sure what caused this signal. There is a slight possibility that it just might originate from an extraterrestrial intelligence. Many unusual signals from space remain unidentified. The study of signals possibly emitted by an extraterrestrial intelligence is a delicate matter that requires a great deal of confirmation.
First, if you think you have a signal from an extraterrestrial, make sure, check with colleagues, double check your data. And then secondly, if you're really pretty sure you found it, tell the whole world.
Despite countless conjectures about a possible contact or some evidence that is being hidden, SETI states that we haven't yet received a confirmed signal and makes it clear that as far as SETI is concerned, it wouldn't be a piece of information to hide.
A lot of people in this country figured the federal government would cover it all up because the public couldn't handle the news. Well, we know that isn't true because we had false alarms. And what actually happens is the media are very interested. The newspapers, the radio shows, TV shows, they call you up right away if you get any kind of interesting signal.
So according to the SETI protocol, the day they confirm the first signal indicative of extraterrestrial intelligence, they will make the news known worldwide. A fact that, considering technological advances, may occur in a short time. Seth Shostak declared before the House Science Committee of the American Congress that in a couple of decades, we will have found evidence of its existence.
The chances of finding it, I think, are good, and if that happens, it'll happen in the next 20 years, depending on the financing. There are sort of guesses as to how many societies might be out there broadcasting, and those guesses run from maybe 10,000 to 1 million. Well, if the correct number is anywhere in that range, then we should find something within a few decades. So, this is not like building cathedrals in the Middle Ages. This is something that's going to work within one generation, if it's going to work at all.
If I had to bet when we will find intelligence beyond Earth, I'd say in the next 20 years. And it's simply because technology is advancing all the time. SETI success depends on computing power.
What will happen from then on? What will occur when we receive a signal and it is confirmed as extraterrestrial? How would that affect our lives, our priorities, our conception of the world, and our own identity? Is humankind prepared?
So what happens if we find a signal? If we find evidence that they're out there, people will still go to work the next day, or if they're in school, they'll still go to school. They won't divorce their spouses. There won't be civil unrest. They won't be rioting in the streets. It's just that we will know something really important, that as wonderful as Earth is, as wonderful as our species is, we're not the only kids on the block. And I think it's good to know that if it's true.
In January 2010, the Royal Society held a conference entitled The Detection of Extraterrestrial Life and the Consequences for Science and Society. The introduction of the conference was as follows. Astronomers are able now to detect planets where life may exist. And the living generation could see the signature of extraterrestrial life being detected. Should it turn out that we are not alone in the universe, it will fundamentally affect how humanity understands itself, and we need to be prepared for the consequences.
Over the long term, if you actually did get a message and could understand it, of course, that could be very transformative. Imagine, giving, I don't know, Neanderthals the keys to your local library. Say, hey, you might want to read some of this stuff. I mean, that would change everything for them. So there is that potential, although I think it's a fairly far-fetched idea.
Concerned that a discovery could be close, humankind has slowly started to prepare itself to establish a protocol procedure. Neither a country nor a collective of people would be represented, but all of humankind.
There's a protocol called the Declaration of Principles Concerning Activities Following the Detection of Extraterrestrial Intelligence. And this provides guidelines about what do we do next. The most fundamental issue raised in this protocol is before there is a reply, there should be broad-based global discussion. That if we are to speak to another civilization, if we are to send a response, it should be a response that has gathered global input. This wasn't transmitted to the SETI Institute or to any other organization. The message was transmitted to Earth. It belongs to the whole Earth. It should be shared widely.
Most scientists agree that a finding like this would alter and transform the status quo in many ways. What would be its effect on our society, our science, our technology, or our religion?
So for me, detecting another civilization is a way of coming to a better understanding of who we are as human beings. It would mean a chance to see whether the ways of knowing that we've developed here on Earth, our math, our science, our ways of expressing ourselves, our music, our art, are they somehow tapping into something that goes beyond Earth, or are they uniquely ours?
The discovery would be on the same level as those of Copernicus and Darwin, and as of the transforming events in human history. However, it will be decades before people get used to the idea that we are not alone in the universe, and its real meaning becomes deeply ingrained, as occurred with the heliocentric cosmology and biological evolution. It's likely that our first contact with an extraterrestrial civilization will happen when the Allen Telescope Array detects a message that confirms, at last, the existence of extraterrestrial intelligent life, or when one of the people connected to the SETI at Home project announces that his computer has decoded some of the signals of the Arecibo telescope. Then, our first contact will be a unidirectional conversation. We might capture some intelligent message by chance, but it could take decades or centuries before our answer gets to them, given the huge distances of the universe.
Let me tell you what my hope for the impact of the detection of a distant technology would be. What I hope is that we can make it understood to the people on this planet that the only way that contact happened was because, on average, technological civilizations have a long lifetime. We're sitting here as a very young technology, and we literally do not know whether it's possible to grow old, to be able to be wise enough to manage our population, to shepherd our planet, to go forward into a long future, long in cosmic times. But if we find someone else, we know the answer to that question. We get a proof of existence. It's possible to grow old. Somebody else figured out how to do it. And I would hope that that would motivate us to find solutions to the problems that we face today. We know that somebody else made it through this bottleneck, this technological adolescence. I'd hope it would motivate us to find answers for ourselves.
Today we know that the first contact may occur in not too a long time. It's not easy to figure out what will happen in this first communication, if it will be something positive or harmful to human beings. What is clear is that it will be a turning point in the life of the human species. Is life an amazing phenomenon exclusive to our planet? Is there life beyond Earth? Humankind has always asked itself this question, but no answer has yet been found. However, thanks to the latest extraordinary advances in astronomy, it appears that we are closer to solving this mystery. State-of-the-art space probes explore planets and moons in our solar system, while sophisticated telescopes scan the universe looking for answers. The results of the research are amazing.
One of the big triumphs of astronomy in the last 2 decades is to show the majority of stars have planets. There are planets all over the place. There are more planets than stars.
These findings have been made possible thanks to the NASA space probe Kepler, whose launch in 2009 marked a milestone in the search for life beyond the boundaries of our solar system. We now know that in our galaxy alone, there are billions of Earth-like exoplanets. Given the vastness of the universe, with more than 100 billion galaxies, it is hard to conceive that somewhere there is no Earth-like planet that can harbor life. Finding it is simply a matter of time.
It's a game changer. It changes what we think about the possibility for life somewhere else. Exoplanets and extremophiles, 2 game changers.
This leads us to think that in apparently harsh environments in our solar system, there is now, or may have been, life. We may find some form of life in the strange methane lakes of Titan, in the oceans hidden under the mysterious icy surface of Europa, in the gigantic geysers of Enceladus, or in the desert plains of Mars.
The second genesis within the same solar system implies that life, the origin of life, is a likely event.
We don't know if the discovery of life will happen first on one of these moons or planets in our solar system, or on an Earth-like exoplanet. But what we do know is that we are closer than ever to unveiling one of the greatest mysteries of nature, whether there is life in outer space. Life, an unbelievably perfect combination of elements able to create living matter. Possibly the biggest mystery of nature. A combination of matter that shows certain attributes that include responsiveness, growth, metabolism, energy transformation, and reproduction.
We don't yet know exactly what life is. We don't have a working definition. Probably my favorite definition is that life is some sort of chemical entity that is self-enclosed and is capable of Darwinian evolution by natural selection.
Some studies state that life may have begun in Earth as early as 4.1 billion years ago. That is still only slightly younger than Earth. a question arises immediately. Is life an exclusive phenomenon of Earth? There's no easy answer to this question. The chemistry of life, begun shortly after the Big Bang, 13.8 billion years ago, during a habitable epoch when the universe was only 10 to 17 million years old. Life may have emerged independently at many places throughout the universe. Or life may have formed less frequently, then spread maybe by meteoroids or comets, between habitable planets in a process called panspermia. In any case, complex organic molecules may have formed in the protoplanetary disk of dust grains surrounding the Sun before the formation of Earth. According to these hypotheses, this process may occur outside Earth on several planets and moons of the solar system, and on planets of other stars, the so-called exoplanets. Since ancient times, humankind asked itself if we are alone in the universe, and if there is life beyond Earth. Those questions may not be easily answered. However, they have always fascinated us.
Astronomers have been interested in the question of life beyond Earth for a very long time. I mean, we can trace back through the ancient Greeks and Romans and Chinese writings speculation about life beyond Earth.
The main issue to search for life in outer space is to establish what are the life support conditions. A source of energy, such as from a nearby star, is needed to drive endothermic or energy-absorbing reactions. Raw materials, predominantly carbon, build and form organic molecules.
So the building blocks of life on Earth, and we know them, there are carbon, hydrogen, oxygen, nitrogen, and others. They are what we are looking on other planets to look for life as we know it.
These building blocks for life, at least as we understand it, are ubiquitous.
Also indispensable is the presence of a liquid or very dense gas as a solvent for biochemical reactions to occur quickly and stably. Liquid water, the life-sustaining universal solvent, at least on Earth, entails certain atmospheric composition and temperatures.
In order to have a habitable environment, you need three things. You need liquid water, and you need organic material, and you need energy. And there are a number of places in the solar system where all three of those things are thought to exist.
Now we already know the key conditions for supporting life. A question arises immediately. How many planets or moons in our solar system meet these conditions? Considering that one of the key prerequisites for extraterrestrial life is the existence of liquid water, there are three candidates in our solar system to have liquid water on its surface. The planet Mars, the Jovian moon, Europa, and the moon of Saturn, Enceladus. Besides Mars, Europa, and Enceladus, which might have liquid water on their surfaces, there is another candidate for supporting life in our solar system, Saturn's largest moon, Titan. Until 2004, Titan remained a great mystery to astronomers, as a dense, opaque haze prevented understanding of its surface. On 2004, the spacecraft Cassini reached Titan and released a small probe named Huygens. That would change everything. These are the images that the Huygens camera recorded as it descended through the haze. Titan's landscape is very similar to Earth's, with mountains, valleys, and plains. When the probe touched down on the surface, it revealed something no one expected. There were pebbles everywhere, similar to the rocks of riverbeds on Earth.
When you're looking at those pebbles, yes, they are rounded pebbles, and they have been rounded by torrents and rivers. But they are not rocks in the sense that we understand. They are actually water ice, so hard that it behaves like rock.
How were these rocks eroded? Is there liquid water on Titan's surface? At minus 180 degrees Celsius, water should be frozen solid. Cassini's radar had the answer. It showed us that Titan's surface has hundreds of lakes.
The big difference, though, is that they are not made of liquid water. They are made of liquid methane.
These two hydrocarbons on Earth are volatile gases. But with Titan's chilly temperatures, they are liquid.
The atmosphere of Titan has methane and ethane and other organic materials that provide a very different kind of chemistry, but a kind of chemistry that is reminiscent of what Earth very possibly looked like before life was abundant.
All these worlds are very far away from the heat of the sun, so they are extremely cold, and some of them are exposed to very high levels of radiation, as they have very thin atmospheres. Therefore, their environments are quite hostile to life. However, life might have found its way.
We also now know about extremophiles, forms of life that live in environmental conditions that when I was a student, I was told, impossible. Can't have any life there. It's too hot. It's too cold. It's too acidic. It's too basic. Too much pressure, too much radiation. They have evolved to thrive in those conditions. So this whole new field of study of extremophiles, it's a game changer. It changes what we think about the possibility for life somewhere else.
Extremophiles such as bacteria that live in high temperature, toxic, deep-sea hydrothermal volcanic vents on Earth offer insight into life that could have developed on other planets that mostly share such extreme, inhospitable environments, which also can include freezing temperatures and minimal sun exposure.
This gave us such a different view of actually what was necessary for life to survive. And all of a sudden, the solar system totally exploded. The horizon of what we call habitability and habitable environment completely expanded in ways that we could not have expected at all.
The chances of finding life on any of these remote worlds in the solar system are now much higher. Finding it is simply a matter of time. Of all 160 or so planets and moons in the solar system, Mars has so far received the most interest from astrobiologists. There are many signs that show that very early in its history, Mars was much like Earth, with large areas of liquid water, a thick atmosphere, ample sources of energy for life, and a good inventory of organic molecules.
In fact, what I like to say when I compare the two planets is that you don't have to invent words to describe Mars. You have mountains, you have canyons, you have polar caps, you have dunes.
There is evidence that Mars had a warmer and wetter past. Dried up riverbeds, vast canyons blasted out by epic floods, valleys carved by raging rivers, polar ice caps, volcanoes, and minerals that form in the presence of water have all been found.
There's a lot of evidence for liquid water earlier in the planet's history, much earlier, about 4 billion years ago, and perhaps some transient water in the time since 4 billion years ago.
But the evidence indicates that all that water disappeared from the surface billions of years ago as Mars cooled down and lost its atmosphere. Did life ever get a foothold on the planet?
As we're looking for evidence for ancient life on Mars, some people think that actually we already had some evidence of that life landing on our own planet. And the best example of that is the Allen Hill meteorites.
We had a piece of Mars here in the lab. We still have it. Allen Hills 84001, a rock that was chipped off Mars by an impact millions of years ago, wound around in space, landed on the Earth in the Antarctic ice sheets, and during the 1984 spring collection season, as that ice was melting and those black rocks were picked up in the melt pools, we realized by the gases that are included in that piece of rock that that's a piece of Mars. And we took it apart at microscopic scales. And we had a big scientific controversy because there were scientists that were claiming features in that rock could only have been produced by biology, and other scientists saying, nope, you can get that with geology.
The search for life on the red planet started decades ago. In 1976, a search for microbial life on the red planet was performed for the first time ever. 2 decades later, in 1997, the Pathfinder mission took a new step forward in this search for life adventure. It found magnesium, aluminum, iron, and phosphate in Martian rocks, which are all possible life-supporting materials. In 2008, the Phoenix spacecraft explored Mars' North Pole. After digging a few inches, it found a white material that evaporated several days later. The analysis of that material revealed it was water ice. Satellites scanned both polar caps and found that there was a lot of water ice under a layer of frozen carbon dioxide. If all that ice ever melted, a more than 80 feet deep ocean would cover the whole planet. The same satellites also discovered that there was ice buried everywhere beneath the desert plains. That was a shocking discovery. Mars had huge amounts of water ice everywhere. But could life exist in the buried ice itself? We now know that there are extremophile microorganisms able to live in similar environments in the dry valleys in the Antarctic here on Earth.
Currently, Mars is very dry and very cold. It's like some regions in Antarctica today, and it's kind of like a very cold desert. So Liquid water would not be stable. If you opened up a container of water, it would immediately evaporate because it's so dry.
Buried ice was found under a layer of dry dirt, as happens on Mars. At the point where the dirt met the ice, there was a thin film of liquid water where extremophiles thrived, just for a short time. These microorganisms remain frozen and dormant most of the year, and they only flourish for a few warm weeks during the summer.
Today, microbes could still live at depth, at some depth, favored by the presence of thin films of water or maybe more liquid water, because the deeper you go, the more the chance that the water could be liquid.
During the Martian summer, it's common to reach 20 degrees Celsius at the equator, so the buried ice might melt and create similar conditions to those found in the Antarctic dry valleys.
Any microbes that might have been there, they're probably living within the rocks or under rock coatings. So that's one of the analog sites that my group's been investigating, is microbes that are living underneath the surface, because that might be viable for Mars as well.
A future mission could eventually prove whether this hypothesis is true or not. But there is another possibility that liquid subsurface water exists on Mars. Mars' huge volcanoes, such as Olympus Mons, could contribute internal heat to sustain subsurface water. This would imply that hydrothermal vents could exist on Mars as well, and therefore it might be also possible that extremophiles, similar to the ones that thrive in the terrestrial hydrothermal vents, might also exist on Mars. However, this is quite unlikely. Everything would change if we were able to find liquid water on the surface. On September 2015, NASA's Mars Reconnaissance Orbiter made an incredible discovery. This spacecraft provided the strongest evidence yet that liquid water flows intermittently on present-day Mars.
It's not pure transparent water. It's very briny water, very salty water, which allows it to remain stable for a little while at the surface, because the pressure at the surface of Mars is very, very small.
Using an imaging spectrometer, researchers detected signatures of hydrated minerals on slopes where mysterious streaks were seen on the red planet. They darken and appear to flow down steep slopes during warm seasons, and then fade in cooler seasons. This finding proved what anyone could have imagined. On Mars' present-day surface, there is liquid water. Maybe in some of those ephemeral streams of liquid water, microbial life has managed to arise. We will have to wait for future rovers and explorers to confirm this hypothesis. What will really change our understanding of the Red Planet are the NASA and ECA missions, both part of the Mars exploration program. Since 2007, the main goal of space missions to Mars was not just to follow the water, whether in the form of ice or liquid water, but to explore its habitability, and above all, to seek signs of life.
The more we investigate Mars, we obtain more clues that the ancient history of Mars was certainly supportive of life, and then that final step of, did life actually evolve? And then if it did, where did it evolve? And what clues are remaining today? Because that was so long ago.
The ultimate aim of missions to Mars is to prepare for human exploration, a step that would really be a new milestone for mankind. The first step in this ambitious exploration program is the ExoMars program, a partnership between ESA and Russia's Federal Space Agency, Roscosmos, with the participation of NASA. Its primary scientific goal will be to search for possible biosignatures on Mars, past or present. ExoMars is a multi-spacecraft program. The first ExoMars mission, ExoMars 2016, is called the Trace Gas Orbiter, TGO. The goal of this orbiter is to study the Martian atmosphere for the presence of methane and other gases, gases that might be linked to some biological processes. The second mission in the ExoMars program is the 2018 ExoMars rover and landing platform. The ExoMars rover is a rover with a 2 meters core drill to sample various depths beneath the surface where liquid water may be found.
The drill was supposed to penetrate the first couple of meters within the sediments. This way it's more probable maybe finding evidence of viable salts.
The third step of this enthralling Mars exploration program is the NASA mission, Mars 2020. The aim of the Mars 2020 rover is to study diverse rocks and soils to understand past habitable conditions on Mars and to seek signs of ancient microbial life. One of its functions is to monitor weather and dust in the Martian atmosphere and test the ability to extract oxygen from the red planet's carbon dioxide atmosphere to prepare for future human exploration. Any of these breakthrough missions might solve the enigma of whether there is past or present evidence of life on Mars. Much further away than Mars, there is another unique world that might harbor life. Our next destination in the search for life is one of the most fascinating Jovian moons, Europa. Europa is one of the 4 largest moons of Jupiter. It's slightly smaller than our moon, and its icy surface is minus 160 degrees Celsius. Virtually everything we know about Europa is thanks to NASA's unmanned space probe Galileo, which passed by Europa 12 times. These were the first images it captured. It is covered by a smooth layer of water ice. In fact, it has the smoothest surface of any known solid object in the solar system.
The surface of Europa is unique in the solar system. It has very few craters, which tells us that the surface is being reprocessed frequently.
Some parts of its surface show blocks of ice that are separated, but seem to fit together like a puzzle. These icebergs could have been shifted by slushy or liquid water beneath.
These cracks probably may extend all the way down to the ocean, to the ocean, or at some point, so you could get some percolation of water.
This peculiar landscape is very similar to sea ice on Earth.
Galileo was able to detect that. All of those things together add up to our picture of how we now know that Europa has a liquid ocean under its surface.
In 1996, the Galileo spacecraft detected a magnetic field on the planet's surface, indicating that there must be some electrical conduction likely to derive from a salty ocean that could be 60 miles deep.
The studies and observations, measurements that have been made in the past decades seems to be converging pretty clearly with the presence of an ocean under the surface of the ice.
So there we have the first key ingredient for life, liquid water. how can water remain liquid at temperatures of minus 160 degrees Celsius? Some sort of mysterious internal heat must be melting the icy crust. Jupiter is the key. Tidal heating from friction due to Europa's eccentric orbit around Jupiter has been proposed.
The ice at the surface of Europa is being cracked. It's not completely sealed. You can see because of gravitational pull and pull, there is this tug of war as Europa is moving around Jupiter. You can imagine that all this friction is creating lots of energy, lots of heat, and then we have good reasons to think that there are hydrothermal system, which means that you have, water being heated by this process.
Volcanoes deep down may harbor hydrothermal vents that provide an energy source to heat and maintain liquid water. So we have two of the three conditions for life: a liquid, in this case liquid water, and a source of energy, that interior heat. We would just need some organic compound, and the chances of life arising would skyrocket. The Galileo spacecraft observed that Europa's ice contains carbon dioxide. When this carbon dioxide is strongly impacted by Jupiter's radiation, it can produce simple organic molecules such as formaldehyde that are steps towards life. The aforementioned tides on Europa could also mix life-supporting substances together in the ocean, but nothing has been proven yet. On 2013, NASA reported a surprising discovery on the icy crust of Europa. Some clay-like materials, specifically phyllosilicates, were detected.
Phyllosilicate just means phyllo, like layered silicate, and these are a fancy name for clays. And clays are a kind of mineral that forms in a lot of water. And on Earth, there are some theories that these clays were some of the original minerals that were present when life was evolving.
According to some hypotheses, the presence of these organic associated minerals may have been the result of a collision with an asteroid or comet. With liquid water, an energy source and the necessary chemical building blocks, perhaps delivered by comets or asteroids, Europa opens up the possibility that life could exist in places never imagined. "12,000 feet beneath the Arctic ice sheets, in complete darkness, there are hydrothermal vents that spew out superheated water with lots of toxic chemicals. Scientists think vents like this could also exist on Europa's ocean floors.
We think that the potentially source of energy for an ocean Europa will be the volcanic activity.
We have recently discovered that clustered around the vents, there are extremophile microorganisms that cover miles of the Arctic seafloor. The discovery of life there really raises the possibility of life on Europa.
Probably Europa might be the best candidate for us to find extant life.
The challenge now is to prove that life has been able to thrive in such a bizarre environment. NASA and ESA have planned 2 different missions to Europa that will investigate its habitability in the next few years.
In 2015, NASA approved a new mission to go to Europa and investigate its environment, and particularly to look for habitability.
NASA's Europa Multiple Flyby mission is a spacecraft that will be launched in the 2020s. The spacecraft will be a highly capable, radiation-tolerant probe that will perform repeated close flybys of the icy moon.
We'll also be looking under the surface to learn more about the structure of the ice shell and the structure of the ocean underneath the shell, using radar and magnetic field detectors and other instruments.
The ESA is developing in parallel its own mission, the Jupiter Icy Moon Explorer, the so-called JUICE mission, that is planned for launch in 2022 and arrival at Jupiter in 2030. This spacecraft will spend at least 3 years making detailed observations, not just of Europa, but also of the giant gaseous planet Jupiter and 2 of its largest moons, Ganymede and Callisto. We will have to wait till the next decade to confirm whether or not there is life on Europa. Europa isn't the only intriguing place this far out in the solar system. Could similar conditions exist on other moons orbiting other planets, even further away from the Sun? Orbiting Saturn, there is a small, mysterious moon that is totally different from the rest of its more than 60 moons. This tiny icy moon, only 300 miles across, is Enceladus. In the last few years, this tiny moon has become the main goal for exobiology, as it has revealed some extraordinary conditions for harboring life.
Most of what we know about Enceladus is thanks to a mission called Cassini. It's a mission that it's been going on for many years. It's an orbiter that has been studying the entire Saturn system and its different moons, but it's been paying close attention to Enceladus.
The Cassini mission offered us a close-up of this remote world for the first time ever. These were the first images it took. The surface is white and glittering, and it is carved with fissures, crests, and cracks. At the South Pole, Cassini made a surprising discovery. It photographed some strange, large cracks, seen here in blue. 4 parallel fissures, scientists named the tiger stripes. They are 75 miles long and hundreds of feet deep. They are similar to fault lines on Earth. After several flybys, Cassini's thermal radar revealed something unexpected. The tiger stripes should be colder than the rest of the moon, as they were in the South Pole. However, they were radiating heat. The fissures were at minus 80 degrees Celsius, which was more than 120 degrees Celsius warmer than the rest of the moon.
It's definitely a place where we see evidence that something profound is happening in terms of potential for habitable environment.
But the most shocking finding was still to come. When Cassini was reoriented, it captured a shocking image. Vast jets of ice were erupting into space.
The camera was able to image plumes of water vapor and ice crystals coming off the south pole of Enceladus.
These actual images showed the plumes were ejecting ice particles hundreds of miles out from the tiger stripes.
Those materials are being ejected through fractures on the surface of the moon, which seem to be connecting the surface with the interior.
However, how this small moon can generate so much heat as to be able to maintain such geothermal activity? Scientists believe that Enceladus might have an internal energy source, like Europa. When it orbits the massive Saturn, friction from gravitational process causes it to heat up, melting ice in the moon's interior in the same way as on Europa. These jets were giant geysers of water that erupted from its icy surface, much like those in geological hotspots on Earth.
Cassini actually has a detector that can fly through the plume, pick up some of the particles and analyze them chemically. And when that detector did its work, it found that some of the particles are salty. And the only way to get salt incorporated into a particle is to have it evaporating directly off of liquid. So that was yet another hint that Enceladus has liquid under the surface from which these plumes are emanating.
But could it prove that under the icy crust of Enceladus existed a subsurface ocean, like on Europa?
We needed even more evidence. The next piece of evidence was from Cassini flying past Enceladus and just carefully analyzing its trajectory as it flew past Enceladus to directly measure how Enceladus's gravity was pulling on the spacecraft. And when that analysis was done, it found a density anomaly under the entire South Pole, indicating that you have a regional sea of water from which these plumes are emanating.
These jets might be connected to active hyperthermal vents at a subsurface water ocean floor, where the moon's ocean meets the underlying rock, a prime potential habitat for life. But there still wasn't anything that could prove life existed underneath that icy crust. The probe spectrometers detected something really exciting. They found in the jets the basic chemical building blocks of life.
So Enceladus is fascinating because, as far as we can tell, it contains the three basic ingredients for life: liquid water, nutrients, and organics.
But does this strange and alien world actually support life? The geysers could provide easy access for sampling the moon's subsurface ocean. And if there's microbial life in it, ice particles from the sea could contain the evidence astrobiologists need to identify them. There are 2 exploration missions proposed by NASA to Enceladus in the near future that would try to find evidence of life in the tiny icy moon. The first one is the Journey to Enceladus and Titan mission. This is an astrobiology mission concept to assess the habitability potential of Enceladus and Titan, moons of Saturn. The second mission, waiting for approval and financing, is the Life Investigation for Enceladus. This proposed mission would capture icy particles from Saturn's moon, Enceladus, and return them to Earth, where they could be studied in detail for signs of life, such as biomolecules.
It's relatively simple, technologically speaking, to send an orbiter to Enceladus that can capture those icy particles in the plume and analyze them in situ or bring them back to Earth for detailed analysis in the laboratory.
Unfortunately, none of these missions have been approved yet. So we will still have to wait to unveil whether or not there is life on this tiny, enthralling moon of Saturn. Close to Enceladus, there is the last of the great candidates for life in the solar system, Titan.
Titan is the largest moon of Saturn. It is one of the largest moons in the solar system, and it is also the only moon that is known to have a thick atmosphere.
Data from the Cassini-Huygens mission, which flew by Titan in 2004, demonstrated the existence of hydrocarbon lakes.
Titan is a fascinating world. It's the most alien place in the solar system, so to speak, because it, in fact, other than the Earth, is the only place we know of that has seas of liquid on its surface, but those seas are not made of water.
In these seas and lakes, there are no waves, as the liquid is liquid methane and ethane, which is much less dense than water liquid. These two hydrocarbons on Earth are volatile gases. But on Titan's minus 180 degrees Celsius temperature, they are liquid. Titan has a very similar landscape to Earth. There are seas, lakes, smoothed rocks on the riverbeds, mountains, valleys, canyons. But these mountains and pebbles are not made by any rock like on the Earth, but they are made of water ice, so frozen due to the minus 180 degrees Celsius temperature on Titan's chilly surface that it behaves like rock. Cassini's radar images showed that on Titan, liquid methane forms clouds, thunderstorms, and even falls as rain.
Methane in the atmosphere also plays a role similar to water in the atmosphere. On Earth, you have a water cycle. On Titan, methane plays a very similar role. It falls to the surface as rain or mist. We do see channels and rivers where methane is flowing across the surface and doing geological work like we would see water do on the surface of the Earth.
Liquid methane has a cycle very similar to Earth's water cycle. The question is, could it behave like water does on Earth, as a liquid that allows organic molecules to dissolve and interact? There is no easy answer to this. Titan's atmosphere also contains many organic gases, such as methane, ethane, and hydrocarbons, and possesses conditions that resemble those of early Earth 4 billion years ago that allowed life to develop.
In many ways, the atmosphere of Titan looks like a young Earth in the fridge, much colder, much cooler. But prebiotic chemistry, the same processes are there. What we don't know is whether these prebiotic processes are turning into something that is biological in nature at the surface of Titan or in the subsurface.
However, liquid methane and ethane are much colder than liquid water by some 200 degrees Celsius, and biochemical reactions would occur at painstakingly slow rates. These compounds are also far less capable as solvents compared to water, and therefore much less life-inducing. Water is also missing from the picture due to freezing temperatures of minus 178 degrees Celsius. Several experiments have shown that with an atmosphere similar to that of Titan and the addition of UV radiation, complex molecules and polymer substances like tholins can be generated, substances that could be considered a sort of precursor to life.
What weirdo chemistry, physics, biology could be. People are trying to think in terms of what could be a biology based on methane. It's not the best, apparently, when it comes to provide a structure for biochemistry.
The conclusion is that Titan is a world rich in organic matter, with a methane cycle comparable in atmospheric and geological processes to Earth's water cycle, that is really likely to harbor life. In the last years, NASA and ESA have combined efforts to develop an unmanned space mission that could finally unveil all the Titan's mysteries, but none of them have been approved yet. One of the most exciting missions proposed to unveil the secrets of the methane and ethane lakes of Titan is NASA's Titan submarine. This submarine would explore the depths of the Kraken Mare, the largest known body of liquid on the surface. This mission would be designed to measure the organic constituents on Titan and would have performed the first nautical exploration of an extraterrestrial sea, analyze its nature, and possibly observe its shoreline. As the other proposed mission to Titan, this Titan submarine mission hasn't been given the green light yet.
There's lots of really fun options for exploring Titan, but NASA has not actually selected one of these options.
Therefore, to date, there are no confirmed space missions to Titan in the coming years. But everything could change if a shocking discovery is made in the near future. Whether or not any of these potential space missions finally reveal the existence of life on Mars, Europa, Enceladus, Titan is an unknown. But what we do know is that now we are much closer than ever to finally finding an answer to the question of whether there is life beyond Earth. "50 years ago, the era of robotic exploration of our solar system was just beginning. In July 1965, the Mariner 4 probe sent the first close-up images of Mars. Those blurred images showed that Mars did not have vegetation, much less canals crisscrossing the planet, as envisioned by earlier generations of astronomers. At that time, the most widespread opinion was that Mars was not just the red planet, but also the dead planet, with the chances for life of any kind being considered infinitesimal. Things have radically changed since 1965, thanks to the extraordinary advances of technology that have led us to use more and more sophisticated space probes to explore our neighbors in the solar system. The three vital factors, energy, liquids, and chemical building blocks, are more widespread than has ever been realized. Now it's not so unlikely to find life beyond the Earth in our solar system. We can't deny that such a huge discovery, even if it were just microbial life, would be really shocking for mankind, as it would imply the first step toward believing that we may not be totally alone in the universe. Then, the right conditions could also exist beyond the boundaries of our own solar system, in distant outer space. Life, an unbelievable, perfect combination of elements that is able to create living matter, may be the biggest mystery of nature. Is life an amazing phenomenon exclusive to our planet? In recent years, we have made several amazing discoveries that suggest that the conditions in our solar system for life might be more prevalent than ever imagined. Recent missions are revealing strange worlds, moons that could have vast oceans concealed beneath miles of ice, like Europa, which orbits around the giant Jupiter. Places where jets erupt hundreds of miles into space, like Enceladus, the tiny Saturn's moon. Or moons with a very Earth-like landscape, with mountains, valleys, clouds, and lakes of liquid methane or ethane, like Titan, the largest moon of Saturn. If life was ever possible, or is now a fact in any of those remote worlds in our solar system, with very harsh and different conditions from Earth, that could imply that life could be possible in any other remote world in outer space.
Second genesis within the same solar system implies that life, the origin of life, is a likely event. If it happens twice in the same solar system, it's likely happening everywhere in the universe.
Now, scientists are searching for planets far beyond the boundaries of our solar system, where we might detect life in the near future. Thanks to the NASA Space Telescope, Kepler, launched in 2009, we know that in our galaxy alone, there are billions of Earth-like exoplanets orbiting their stars. Given the vastness of the universe, with more than 100 billion galaxies, it is hard to conceive that somewhere there is no Earth-like planet that can harbor life.
Unless something very unusual happened here on Earth, then life is developed on thousands of millions of planets just in our galaxy, right? If it's not a miracle, then it's all over the place. That's the bottom line.
In recent years, thanks to Kepler, we have confirmed dozens of Earth-like exoplanets that might harbor life, and even intelligent life waiting to be discovered. We don't know if the discovery of life will happen first on one of these moons or planets in our solar system, or on an Earth-like exoplanet. But what we do know is that we are closer than ever to unveiling one of the greatest mysteries of nature, whether there is life in outer space. Is there life beyond Earth? Humankind has always asked itself this question, but no answer has yet been found. It appears that we are closer to solving this mystery. Recent discoveries have uncovered planets beyond our solar system that are believed to be similar in many ways to Earth.
If I got to ride on a spaceship to one planet that we found with Kepler, the one that I would go to is Kepler-186f. It's one of the smallest ones. It's at the right temperature that liquid water could exist on its surface.
Kepler-186f is the first validated Earth-sized planet to orbit a distant star in the habitable zone where liquid water might pool on the planet's surface. The discovery of Kepler-186f confirms that Earth-sized planets exist in the habitable zones of other stars and signals a significant step closer to finding a world similar to Earth. Kepler-186f orbits its star once every 130 days and receives 1/3 the energy that the Earth does from the Sun, placing it near the outer edge of the habitable zone. If you could stand on the surface of Kepler-186f, the brightness of its star at high noon would appear as bright as our Sun is about an hour before sunset on Earth.
Today, when we take a look at what we know about the origins of life on this planet, it leads us to think that the same things that happened here might well have happened elsewhere. And so life beyond this planet is quite plausible in terms of the science that we know today.
We now know there are 4 important candidates in our solar system to harbor life. Mars, Jupiter's moon Europa, and Saturn's moons Titan and Enceladus. On every of them, we can find all of the 3 key ingredients for life: organic compounds, a liquid, and an energy source.
There is water on Mars under the form of ice at the poles and under the surface, but it is also flowing from time to time at the surface during spring and summer.
Although there's no evidence of any form of life on Mars yet, scientists think it might be found soon. On Jupiter's moon Europa, 2 of those key ingredients can also be found.
We do know there is water on Europa. On the surface of Europa, we have an icy crust. This icy crust has been observed using Voyager spacecraft, but also the Galilean spacecraft in the 90s.
Under an eerie water-ice crust, 10 to 30 kilometers thick, that covers this tiny moon, there's supposed to be a liquid ocean, which may be about 100 kilometers deep. The Saturn's moons Titan and Enceladus have become the search for life priority top spots in the recent years.
Titan is the only moon in the solar system that is known to have an atmosphere. It's also the only place in the solar system that has an atmosphere made primarily of nitrogen, except for the Earth. So Titan and Earth are closely linked in that way.
Titan is a fascinating world. It's the most alien place in the solar system, so to speak, because it, in fact, other than the Earth, is the only place we know of that has seas of liquid on its surface, but those seas are not made of water. They're made of liquid methane and liquid ethane.
Titan is the only place in the solar system outside Earth where there are stable bodies of surface liquid. But at minus 180 degrees Celsius, this liquid can't be water. We know there are lakes filled with super-chilled liquid methane and ethane. In recent years, Enceladus, a tiny moon orbiting Saturn, has become one of the main goals for exobiology. Enceladus is a small icy moon, quite similar to Europa, as it has a thick icy crust and an ocean beneath. We know there are vast jets of water ice erupting several miles into space.
Enceladus is one of the most interesting places in the solar system because of the presence of this activity, this geyser-like activity. If we have geyser-like activity, people expect to have water, liquid water.
Recently, in those jets, some of the basic chemical building blocks of life have been detected, so we can be sure that we have on Enceladus the trifecta to harbor life: liquid, organic compounds, and an energy source. But if life was able to emerge in any of those remote and harsh worlds, why couldn't it also arise on any other planet far beyond the boundaries of our solar system?
Second genesis within the same solar system implies that life, the origin of life, is a likely event. If it happens twice in the same solar system, it's likely happening everywhere in the universe.
If we were able to find life within our own solar system on another place, and furthermore, be able to say that it developed, independently, then you're saying within the same stellar system, you had life evolve twice. And the conclusion from that is that life forms very easily.
A generation ago, just the idea of a planet orbiting a distant star was still in the realm of science fiction. So, to think of the possibility of life on a planet like that was simply unimaginable. In fact, the first exoplanets weren't discovered till 1992. That very year, 2 super-Earth exoplanets were found around pulsar PSR 1257+12 at a remote distance of 2,300 light-years away. This announcement shocked the scientific community at that time, as it was the first multi-planet extrasolar system ever discovered. Could any of these super-Earth harbor life? Unfortunately, a pulsar is a very different kind of star from the Sun. In fact, it's a dead star, formed when some of the largest stars in the universe exploded as supernovae.
A pulsar, which is what's left after a star, a really massive star explodes, and you've got this thing which is one step away from being a black hole. While this was really exciting, it was hard to tell what it meant because pulsars are so much different from normal stars.
These may not seem at first to be good places to look for habitable planets. Supernovae are, frankly, quite apocalyptic events that would easily vaporize any ill-fated planets in orbit around the exploding star. That distant world would be bathed in a lethal cocktail of X-rays and charged particles emitted by a star so faint in visible light that it would scarcely cast a shadow on this world's surface. so the chances of life arising in such a weird and hostile environment would be remote. However, the real importance of this discovery was that for the first time ever, the existence of planetary systems beyond the limits of our solar system was confirmed. If we found 2 exoplanets out there, why couldn't there be many more? We had to wait 3 more years to find an exoplanet orbiting a sun-like star, which was far more important because the conditions of such a planet would be potentially similar to any of the planets in the solar system. On October 6, 1995, was the announcement of the discovery of the first planet orbiting a sun-like star in the journal Nature. That star was 51 Pegasi, a sun-like star located 51 light-years away, and the exoplanet was a giant planet.
The first exoplanet found around a star like our own was called 51 Pegasi b. Very unusual. It's a very large planet. It's bigger than Jupiter. It's more massive than Jupiter. And it's on a very short period orbit. It goes around its star. 1 year on this planet takes 4 days. It's a very short amount of time.
That discovery marked a turning point in the search for exoplanets. From that moment on, many new ones were found. Nevertheless, what radically revolutionized the search for exoplanets was the NASA Space Telescope Kepler.
Before Kepler was launched, there was hundreds of planets that we knew of in systems around other stars, and now we know of thousands. And that's why Kepler was so revolutionary.
The Kepler was a space telescope specifically designed to survey our region of the Milky Way galaxy to discover hundreds of Earth-sized and smaller planets in or near the habitable zone of their respective stars and determine the fraction of the hundreds of billions of stars in our galaxy that might have such planets.
It works very simply. I mean, anybody can understand this. It's just staring at one spot on the sky all the time, never blinks. And it's looking at 150,000 stars. And it just monitors how bright they are, kind of like a camera light meter, really. And occasionally they'll see this star over here, for example. It'll get a little bit dimmer, a very fraction of a percent dimmer for a few hours, and then it'll get bright again. Well, that happens if a planet passes in front of that star.
We've gone from finding 100 planets to over 1,000 planets with Kepler, those that have been confirmed. And there's about 3,000 or 4,000 more which we have strong evidence for, but we wouldn't consider confirmed planets just yet.
Kepler is on the hunt for planets. Kepler has found literally thousands of planets or planetary candidates. It's a planet-finding machine.
In 2011, for the first time ever, Kepler provided scientists with a census of the Milky Way, so we could calculate how many stars in the Milky Way could have a planet like ours. Around 1 billion.
Maybe there are 1 million, maybe there are 1 billion, maybe there are 100 billion planets in the Milky Way galaxy that could support life, the kind of planets that earthly life could survive on. How many of them have cooked up their own life? And we don't know the answer to that, okay? Because that depends on how hard it is to get life started. Just because I give you all these, these worlds doesn't mean that life will get started. But on the other hand, those planets are all made out of the same stuff that Earth is. So again, unless something very unusual happened here and nowhere else, there's going to be biology all over the place.
Just 4 years after its launch, on April 2013, the Kepler team reported one of their first great triumphs, the discovery, for the first time ever, of 2 exoplanets very similar to the Earth, Kepler-62e and Kepler-62f. This discovery created great enthusiasm, as it implied the confirmation of Earth-like planets where life might be possible. Each of these planets have a radius 1.6 and 1.4 times of Earth and orbits Kepler-62, an orange dwarf star, in its circumstellar habitable zone. A modeling study also concluded that Kepler-62e and Kepler-62f are likely covered mostly, perhaps completely, in water. Kepler-62e probably has a very cloudy sky and is warm and humid all the way to the polar regions. Kepler-62f would be cooler, but still potentially life-friendly. Unfortunately, they are at a huge distance of 1,200 light-years away in the constellation of Lyra. Thanks to the Kepler mission, we now know that there are tens of billions of planets orbiting stars just in our galaxy, the Milky Way, and we know there are billions of galaxies across the universe. So if in just one planetary system like ours, life arose on one planet, and there are at least 4 more candidates, the likelihood of finding a planet in outer space that could harbor life should be very high. But Kepler has discovered for us not only the existence of Earth-like planets, but also has provided us with amazing data about the universe, such as the confirmation of the existence of planets that orbit around not only 1, but 2 stars, like Kepler-16b. This planet was Kepler's first discovery of a planet that orbits 2 stars, what is known as a circumbinary planet.
So one of the most exciting discoveries from Kepler was that we were actually able to find planets around binary stars. And the first one that was found was Kepler-16b.
Kepler-16b is many people's favorite planet that was discovered with Kepler. It orbits around not 1, but 2 stars at the same time. This was something which was predicted not to exist. 2 stars setting at the same time was just a piece of science fiction. But the universe is stranger than what scientists can imagine, and it turns out that this sort of thing is true.
Since 1992, over 2,000 exoplanets have been discovered. Thanks to future Space Telescope missions planned for launch, the number of observed exoplanets is expected to increase greatly in the coming years. Despite having discovered just a tiny fraction of all of those billions of exoplanets that we think that exist, how could we know how many of them could harbor life? In astronomy and astrobiology, the region around a star where a planet with sufficient atmospheric pressure can maintain liquid water on its surface is known as the circumstellar habitable zone.
The habitable zone is a place, it's kind of a way of thinking about the right way to go look for planets like our own.
The Earth is obviously in the circumstellar habitable zone of our solar system. A potentially habitable planet implies a terrestrial planet with conditions roughly comparable to those of Earth, and thus potentially favorable to life.
There's a sweet spot, an area where it's not too hot and not too cold, and we call that the habitable zone, or some people call that the Goldilocks zone. If you've got a planet in that regime, and if it's small, if it's rocky enough, and it had water, that water would be in a liquid state, more than likely. So that would be a good place to go looking.
On November 2013, astronomers reported, based on Kepler space mission data, that there could be as many as 40 billion Earth-sized planets orbiting in the habitable zones of sun-like stars and red dwarfs just in our galaxy, the Milky Way, 11 billion of which may be orbiting sun-like stars. Those 11 billion exoplanets orbiting stars like our Sun really are a huge number of potential Earth-like worlds. However, now we know that stars very different from our Sun may be a good place to look for life. In May, 2016, a team of astronomers announced, for the first time ever, the finding of 3 habitable planets orbiting a star completely different from ours, an ultra-cool dwarf star. It's the first planetary system found around a star like this. The star, named Trappist-1, is just 40 light-years away and is much cooler and redder than the Sun, and barely larger than Jupiter. In fact, stars like this are very common in the Milky Way, and they are very long-lived. The 3 planets are very similar in size to the Earth and might have habitable regions on their surfaces. So the answer to what the best place in the universe is to find life nowadays has radically changed. To date, among all of the more than 1,000 confirmed exoplanets, there are around 50 that are in the circumstellar habitable zone of the star they orbit around. And therefore, they could be potentially considered Earth-like planets, which does not imply these distant worlds may harbor life. However, could life be possible outside those habitable zones? The discovery of hydrocarbon lakes on Saturn's moon Titan has begun to call into question the carbon chauvinism that underpins circumstellar habitable zone theory. Liquid water environments have been found to exist in the absence of atmospheric pressure and at temperatures outside the circumstellar habitable zone temperature range.
Just because a planet is outside the habitable zone doesn't mean that it couldn't have life.
For example, Saturn's moon Enceladus and Jupiter's Europa, both outside the habitable zone of our solar system, may hold large volumes of liquid water in subsurface oceans. If we are considering the possibility that life could arise in such harsh environments, which are not in the circumstellar habitable zone, that implies that we should look for exoplanets far beyond those zones. So the chances of finding an exoplanet with conditions to support life are much higher. We know that it's not an easy task to study and analyze the planets and moons of our own solar system, as they are millions of kilometers away from Earth. However, exoplanets are not just millions of kilometers away, but many light years away from Earth. How can astronomers manage to study exoplanets if they are trillions of kilometers away? There are several methods used by astronomers and astrobiologists to discover and to study these extremely distant, mysterious worlds. Before the launching of the Kepler mission in 2009, the most successful technique for detecting exoplanets was the Doppler spectroscopy, also known as the radial velocity method. The radial velocity method relies on the fact that a star does not remain completely stationary when it is orbited by a planet. A planet is much smaller than its star, but it still exerts a tiny gravitational pull or tug on the star as it orbits. When a planet is behind the star, from our point of view, it pulls the star slightly away from us. When it's in front, it pulls the star slightly toward us. This causes the star to wobble back and forth. Astronomers look for this wobbling to find planets. They use something called a spectrograph and powerful telescopes to examine the light coming from a star. A spectrograph, like a prism, splits the light from the star into its component colors, producing a spectrum. Some of the starlight gets absorbed as it passes through the star's atmosphere, and this produces small, dark gaps or lines in the spectrum. As the star moves closer to us, these lines shift toward the blue end of the spectrum. As the star moves away, the lines shift back toward the red end of the spectrum. So the spectrum appears first slightly blue shifted and then slightly red shifted. Therefore, astronomers can look for orbiting planets by looking for these back and forth motions of the lines in a star's spectrum.
And you can work out from the speed that's being pulled towards you and how long it takes to go around in that circle, you can work out the mass of the planet or the companion thing which is pulling it around. If that mass is very small, the thing is a planet. That method has been very successful. It found most of the planets which were discovered early on.
However, the Kepler technique was based on the planet's transit. The transit method is based on the observation of a star's small drop in brightness that occurs when the orbit of one of the star's planets passes. Transits in front of the star. The amount of light lost depends on the sizes of the star and the planet, and the duration of the transit depends on the planet's distance from the star and the star's mass.
With the Kepler Space Telescope, when we look at a star, we don't see the planet directly. All we see is a tiny dip in the brightness of the star when the planet passes in front of it. From the size of the dip, we can work out the relative size of the planet. Is it a big planet or is it a small planet?
The combination of transit photometry and Doppler velocimetry reveals planetary radius, mass, and density, which are some of the main parameters to evaluate the potentiality of the exoplanet as an Earth-like candidate, and so to harbor life.
Once you know the distance away from the star and you know how hot the star is, you can estimate what the temperature on the surface of the planet would be like.
Another of the main parameters to analyze the Earth-like potential of an exoplanet is its atmospheric composition. Atmospheric studies of exoplanets might be performed with spectroscopy during planetary transits. During the transit, the stellar light passes through the atmospheric limb of the planet. Spectral analysis of this filtered light reveals the structure and composition of the atmosphere. Astronomers could identify the most Earth-like exoplanets by detecting the biomarkers, which are the imprints that life forms have on their host planet atmosphere. For instance, the molecular oxygen that we are breathing results from the presence of life on Earth. Unfortunately, with present-day technology, it's extremely hard to closely study the atmospheric composition of those remote planets.
The main thing that's keeping us from being able to do that now, of course, is technology. We don't have the technology, in functioning instruments at the moment to be able to do that effectively. But that's something that will change with other missions in the pipeline, like Jack Webb Space Telescope and other missions that are happening.
Kepler continuously monitors over 100,000 stars similar to our Sun for brightness changes produced by planetary transits. Thanks to this ingenious technique, Kepler has confirmed to date more than 1,000 exoplanets. Scientists think that about a few dozen of them can be labeled as Earth-like. Considering the possibilities of finding an Earth-like exoplanet are much higher in the circumstellar habitable zone of its planetary system, the planet hunting then started to focus on those areas. One of the first discoveries was 70 Virginius b, an exoplanet located approximately 60 light-years away in the constellation of Virgo. 70 Virginius b was located exactly in the middle of the circumstellar habitable zone of its planetary system, so it was supposed not to be too hot or too cold. Unfortunately, further studies reported that this remote world was a gas giant with very high temperatures, which ruled out any potential for liquid water and therefore of life. The early findings were discouraging in terms of detecting an Earth analog. But this was just the beginning. In 1998, a discovery made in the star Gliese 876, a red dwarf located in the constellation of Aquarius at a distance of 15 light-years away from Earth, really encouraged astronomers. A gas giant was detected in its habitable zone. Gliese 876b. Three years later, another gas giant closer to this one was found, Gliese 876c. We know that life as we know it is not possible on gas giant planets such as Jupiter or Saturn. But the big surprise was that both exoplanets may have habitable moons orbiting around them, as Jupiter and Saturn have.
This was one of the first planets to be discovered in the habitable zone, and people theorized that if it had a moon around it, the moon would be rocky, and the moon would be the right temperature to have liquid water.
Why couldn't any of these hypothetical moons around Gliese 876b and c harbor life, as we hope Jupiter's moon Europa or Saturn's moons Titan and Enceladus might?
So it's an exciting place to think about, and maybe an exciting place to look for in the future.
After the discovery of these exoplanets with potential Earth-like moons, several similar exoplanets with moons orbiting around them were discovered. Maybe on any of those remote moons, life arose in the past, or exists in the present, or might appear in the future. After all these early discoveries, we started to approach to the main goal, to find the most Earth-like world. An Earth analog, also referred to as a twin Earth or Earth-like planet, is a planet or moon with environmental conditions similar to those found on the planet Earth. If life could arise on Earth millions of years ago, and if we look for exoplanets similar to our planet, the chances of finding habitable planets skyrocket. Recent discoveries have uncovered planets that are believed to be similar in many ways to Earth, with relatively high Earth similarity indexes. The size is often thought to be a significant factor, as planets of Earth size are thought more likely to be terrestrial in nature and be capable of retaining an Earth-like atmosphere.
From the point of view of Kepler, a planet is Earth-like if it's small enough that it's probably rocky. It's not a gas giant like Jupiter or Saturn.
But size alone is a poor measure, particularly in terms of habitability, because next to us, there is a planet with a very similar size and mass, Venus, where it is almost impossible for life to arise. There are other criteria to be considered, like the surface gravity or the star size and type.
Our planet is Earth-like if it's the right distance away from its star, that it's in the habitable zone, that it's not too close that it's too hot and all the water that it would have would boil away, and not so cold that if there was any water on it, it would all freeze to ice.
If we are able to examine all of these parameters of an exoplanet, we would be able to know if it is or not a real twin Earth.
So when we say Earth-like for Kepler, we usually just mean that it's small enough that we think that it's solid enough that you could stand on it, but that doesn't mean that it has an atmosphere or that it has an ocean.
It's also often cited that an Earth analog must be terrestrial. That is, it should possess a planetary surface composed of materials similar to Earth's. The conclusion would be that extrasolar planets, or moons, in the center of its circumstellar habitable zone, the so-called Goldilocks position, with substantial atmospheres, may possess oceans and water clouds like those on Earth. In addition to surface water, a true Earth analog would require a mix of oceans or lakes and areas not covered by water.
We believe that water is essential, but just about everything else you can think about, which is important for life, there seems to be life on the Earth that doesn't need it. There is life that survives without sunlight, there's life that survives without oxygen, there is life that survives deep down underneath the ice in Antarctica.
Unfortunately, with the present technology, we can't properly evaluate most of the parameters like the temperature, the atmospheric composition, or the surface of the exoplanets. Nevertheless, considering we have already discovered hundreds of exoplanets, we can't help but wonder if a real Earth analog has already been discovered. On 18th April 2013, astronomers from the Kepler team announced a discovery that created great expectation. For the first time ever, two very Earth-like exoplanets were found. They were the Kepler-62e and the Kepler-62f. And orbits Kepler-62, an orange dwarf star, in its circumstellar habitable zone. They immediately became prime candidates to host alien life. A modeling study also concluded that Kepler-62e and Kepler-62f are likely covered mostly, perhaps completely, in water. Kepler-62e probably has a very cloudy sky and is warm and humid all the way to the polar regions. Kepler-62f would be cooler, but still potentially life-friendly. Unfortunately, they are at a huge distance of 1,200 light-years away in the constellation of Lyra. Soon after, it was discovered an exoplanet even more similar to Earth, Kepler-186f. This finding was a milestone, as it was the first rocky planet found in the habitable zone of its system. It is 492 light-years away from the Earth.
Kepler-186f is possibly my favorite planet to come out of the Kepler mission. It's a small planet. It's maybe 10 to 20% bigger than the Earth. Based on everything we know about planets, it's almost certainly to be rocky. And it's the right distance away from its parent star that, if the atmosphere is right, if the greenhouse effect is right, it could have liquid water on the surface.
After that discovery, several more Earth-like candidates started to arise, like Kepler-438b, Kepler-452b, or Kepler-440b. All of them were very similar to our planet, but none of them was a real twin Earth. But everything changed on July 23, 2015. That day, NASA's Kepler Space Telescope science team shocked the scientific community with an amazing finding. The most Earth-like planet ever was discovered. Its name, Kepler-452b. What made different this one to the other previous Earth analog candidates? Kepler-452b is the very first, apparently rocky planet that orbits a G-type star like our Sun.
It's a planet in the habitable zone around a star which is almost a clone of our own Sun.
After this discovery, the Earth is a little less lonely in the universe. Kepler-452b circles its star, which is about as hot as our Sun, 10% brighter and 20% larger, at an orbital radius just 5% larger than that of the Earth. A year on this planet is 385 Earth days long, just 20 days longer than Earth's.
What makes this slightly less exciting from the point of view as could it be habitable is its size. Our best guess at the size is that it's about 60% bigger than our own Earth.
It is the smallest Earth analog planet ever found in the habitable zone of a G-type star like our Sun. Previous research on super Earth-sized planets like 452b suggests this one has a good chance of being rocky. If it is a rocky world, it'd weigh in at about 5 Earth masses, giving it a surface gravity of roughly 2 grams, which would mean that our weight would be double on its surface. Kepler-452b could have a thick, cloudy atmosphere and volcanic activity. Even more exciting than Kepler-452b's Earth-like demeanor is the fact that this world has spent around 6 billion years in the habitable zone of its star. That's considerable time for life to arise somewhere on its surface or in its oceans, should the conditions for life exist. Kepler-452b is about 1.5 billion years older than the Earth. If it was Earth-sized, the planet and its aging, brightening star might be at a point in their evolution where liquid water would be rapidly evaporating from the surface. But because of its higher mass, astronomers believe Kepler-452b could continue to hold liquid water for the next 500 million years or so. So far, it's the only known world in the system, which lies some 1,400 light-years away in the Cygnus constellation. Obviously, we're not going to get there anytime soon, but it's fascinating to imagine that far off in the distant reaches of space, a world very much like our own might already exist. If this twin Earth exists, why couldn't thousands more like it exist? Less than a year after the amazing finding of Kepler-452b, on May 2016, a new discovery shocked the scientific community. Astronomers using telescopes at European Southern Observatory in Chile discovered 3 planets around a dim dwarf star just 40 light-years from Earth in the constellation of Aquarius. These worlds may be the best targets so far found in the hunt for life elsewhere in the universe. They used the Trappist telescope to monitor the brightness of an ultra-cool dwarf star in the constellation of Aquarius, which has been named Trappist-1. Trappist-1 is much cooler and redder than the Sun and barely larger than Jupiter. Stars like this are very common in the Milky Way, and they are very long-lived. This was the first time that planets have been found around one of them. The 3 planets are very similar in size to the Earth and might have habitable regions on their surfaces. But the really exciting result is that these are the first Earth-like planets that are well suited for the detection of life. The ultra-cool dwarf stars are the only places where life could be detected on an Earth-sized exoplanet using our current technology. The light from much brighter star, like the Sun for example, would swamp vital measurements of the atmospheres of any candidate planets. The next step is to make more detailed observations using the next generation of telescopes, such as ESO's, European Extremely Large Telescope, and the James Webb Space Telescope. That will allow astronomers to study the atmospheres of planets like this and to search for molecules related to biological activity, like ozone, methane, or water. Although there is not yet any proof of the existence of life on all of these exoplanets that we've already found, even in the most Earth-like of them, like Kepler-452b, we can't help but wonder if any of those potential forms of life that might have arisen there were or will be able to evolve into intelligent life. If any of those extremely remote worlds was formed billions of years ago, as Earth did, and it became into a habitable planet, then the organic compound had time enough to mix up and organize into living forms. Perhaps any of those living forms might have evolved into complex forms of life, and some of those complex forms of life might evolve into intelligent beings with consciousness. Thanks to Kepler mission research, it's known that just in our galaxy, the Milky Way, there might be millions of Earth analogs, and there are billions of galaxies across the universe. So the chances are much higher than we could have ever imagined. For that reason, science is carrying out an intense search for intelligent life. The SETI Institute in California is nowadays the main world institution devoted to the search for extraterrestrial intelligence. Its name, SETI, stands for Search for Extraterrestrial Intelligence. This search is based on the use of radio telescopes. Radio telescopes receive radio waves. As we can't go to space aboard spacecrafts to find that intelligent life, what we look for are radio signals.
What we're looking for is a signal that's at one spot on the radio dial. Just like when you're listening to the radio in your car. You know, you tune across the dial, you hear static everywhere, and then at one spot you're near, and there's a station. Okay, that's the signal that's produced by a transmitter somewhere. It's not natural static. It's not like a quasar or a pulsar or galaxies or hot gas, cold gas. All those things in space make radio noise, but it's all over the dial. So we look for signals that are at one spot on the dial, and of course the source of the signal has to be up in the sky. Those are the kinds of criteria we use to know that even if we don't know what it means, we at least know they're there. They're on the air.
Unfortunately, till now, we haven't received a signal that can be really attributed to extraterrestrial intelligence. In the coming years, NASA and ESA, the European Space Agency, have planned to launch several space telescopes that will surely help to unveil the mystery of life beyond the boundaries of our solar system. The most ambitious one is the James Webb Space Telescope. This project is an international collaboration between NASA, ESA, and the Canadian Space Agency, CSA. It will be the premier observatory of the next decade, serving thousands of astronomers worldwide. It will study every phase in the history of our universe, ranging from the first luminous glows after the Big Bang to the formation of solar systems capable of supporting life on planets like Earth, to the evolution of our own solar system. This new telescope, 3 times more powerful than Hubble, will be able to analyze starlight passing through the atmospheres of the closest Earth-like worlds, looking for the telltale signs of life itself, like, for instance, detecting gases in its atmosphere usually linked to life processes such as oxygen, methane, carbon dioxide, or nitrogen.
JWST is really going to help us understand what atmospheres of planets are like under different conditions, and that's going to be a really exciting result.
There is another mission, the CHEOPS mission. CHEOPS comes from characterizing exoplanet satellite. This is an ESA mission dedicated to searching for exoplanetary transits by performing ultra-high precision photometry on bright stars already known to host planets. With all of these new space telescopes programmed to be launched in the coming years, we are sure that finding a habitable exoplanet and any consistent biosignature will be just a matter of time. If we are ever able to find evidence of the existence of any form of life among one of those billions of exoplanets we know are across the observable universe, it would be undoubtedly shocking.
If we did find life somewhere else in the solar system and we were able to do, for example, a genetic analysis to determine that it was distinct from life on Earth, that would be a really earth-shaking discovery.
Living generation might be witness of a finding that would undoubtedly be a turning point in the history of humankind. The discovery of life in outer space.
Our sun is a second or third generation star, formed by the remains of gas and dust from other stars that have already died. Everything that surrounds us, animals, the air we breathe, the water we drink, is composed of atoms that were created inside the stars. We are made of star stuff. This idea invites us to think that life on Earth is not an isolated phenomenon. But this idea could be incomplete. Recent scientific findings highlight an even deeper and disturbing idea. The role of the stars doesn't stop there. Not only do they create matter, the atoms that make living things, they may also be responsible for creating, evolving, and extinguishing life anywhere in the universe. But the question is, how can so distant stars be associated to our lives? What kind of cosmic link binds us to them? To search for answers, we begin a journey that will take us to some of the best research centers in the world. Here begins an adventure to discover a natural phenomenon hidden from our eyes, the cosmic radiation. An exciting world where astronomy meets particle physics and biology. In the cosmic radiation, we are looking for the link between life and the most distant stars. Perhaps stars bring more than just matter that we're made of. Perhaps we are not only star stuff. We begin our journey in southern Europe. This is the German Hispanic Astronomical Observatory at Calar Alto in the south of Spain. The dry and sunny climate of this region provides an ideal place for observing the sky. From here we can find that the stars are ovens where many of the atoms that make up living things are made. Anne is one of the scientists working in this complex.
With the help of the telescopes that we have here at Calar Alto, we can detect and investigate what the stars are made of, what elements they're composed of, and what elements are being formed in these stars.
These types of telescopes, which collect visible and infrared starlight, have been fundamental throughout the 20th century, and with their help, we know that stars do not live forever.
Stars are objects that evolve. The stars are objects that are born, have a life, and then of course they die. It will happen to our sun. It was born, has its life, now is in middle age, and within 5,000 million years will die too.
The universe is filled with regions where hydrogen and other heavier atoms in dust form accumulate. They are very special places where one of the most beautiful sky phenomena occurs: the birth of stars.
Stars are formed in clouds of dust and gas that begin to agglomerate and coalesce because of gravity. They begin to bond, and then there is a moment when this union generates such high energy and temperatures that the most elemental atoms, the hydrogen atoms, begin to merge and form more complex atoms.
The great energy inside stars allows for the creation of new and heavier atoms by nuclear fusion. Helium, carbon, oxygen, silicon, and iron are formed in gigantic stellar ovens. At the end of their lives, the stars explode as supernovae and novae. They release all those atoms into space. This stellar dust and gas is the raw material to form new stars and planetary systems.
Our star, the Sun, is not a first-generation star that was formed early in the universe. This star has been formed in an enriched media, in a medium already formed by elements that have come from other stars.
Behind these facts, a disturbing idea appears, a thought that sets us as a part of the cosmos.
The same way that the stars and other planets are formed by these elements created inside other stars, everything in this planet, all the living things, is formed by the same atoms that once were inside the stars.
We are star stuff. Life as we know it is grounded on atoms formed in stellar furnaces. But science has gone a step further. The latest findings suggest that the relationship between the stars and life in the universe is even deeper. During the death of stars, large amounts of energetic particles are also ejected into space. These tiny cosmic bullets are known as cosmic rays. Pieces of atoms are released into space at nearly the speed of light. The effects of these cosmic rays on life are disturbing, and now, for the first time, we can see a cosmic relationship which we couldn't imagine. But if we want to discover what is behind the cosmic rays, we have a serious problem. Telescopes, like those in Kepler-Alto, detect the light emitted by stars. Light, energy as photons, which we can also see with our own eyes. Almost all telescopes which scientists have built in the 20th century are based on the detection of photons. Some detect visible light or infrared, also at higher or lower energies, as it happens with X-rays or radio waves. But none of these advanced telescopes can help us in finding the cosmic rays that flood the universe. To detect particles passing through our atmosphere at nearly the speed of light is something quite different. We need new and advanced instruments. We need a new way of doing astronomy. In the province of Mendoza in Argentina, the international scientific community has built the largest observatory in the world for the detection of cosmic rays. The Pierre Auger Observatory, a detection instrument as extensive as 600,000 football fields in one of the flattest and isolated places in South America. From here, we will be able to discover what they are and how to hunt cosmic rays. This is a spark chamber, a device to detect charged particles. When a charge passes through the chamber, it generates rapid emission of light, which reproduces the path of the particle. Every time we see the pink spark, it means that a new particle has passed through the chamber. The particles are so energetic that they can pass through the chamber like a bullet through a piece of paper.
This is a spark chamber. What it does is every time a particle passes through it, it leaves this trail, which is a sort of spark like you see in a lightning. Actually, as the efficiency of this instrument is not very, very big, I mean, there are much more particles which is hitting us than you can see.
But no one in this lab sends particles into the camera. Moreover, no matter where on Earth we place the camera, in a desert, in a city, or in the ocean, in the equator of the planet or at the poles, the camera always detects charges.
Actually, none of us, if you want to be free of this, you may have to hide in deep tunnels. Anything, any place you are in the surface of the Earth, you'll be submitted to this radiation which is coming from outer space.
The charges that we trace with the spark chamber are cosmic rays. But despite their name, they are not light rays. Rather, they are subatomic particles, tiny bits of matter raining down from the sky at nearly the speed of light. Its enormous power allows them to reach the surface. There, they cross the rocks, water, and living things. But they are invisible. We need special equipment, like the spark chamber, to make out that they are there. Because of this invisibility, and at the same time continuous presence anywhere on the planet, the story of his discovery is worth telling. At the beginning of the 20th century, scientists opened the doors of an unknown and magical world, the internal structure of atoms. They used to chase electrons, protons, and all kinds of new subatomic particles. But in their experiments, they found something inexplicable. Ron Shellard knows this fascinating moment in history very well.
They began to realize, scientists began to realize that there was always a little awkward thing. The charge would leak slowly.
In this simple electroscope, two metal sheets are hanging from a rod. By placing an electric charge on the rod, the two sheets are separated because they have equal sign charges. The sheets' weight pushes them into their initial position, but as the charge remains, the electrical repulsion keeps them apart. However, bit by bit, and in front of the astonished eyes of scientists, the sheets started to discharge for no reason. No matter how isolated the experiment was, at the end, they ended up in the initial position. What was happening? Why was the charge disappearing?
By the beginning of the end of the 19th century, the beginning of the 20th century, scientists realized that nature had radiative materials.
Some radioactive materials emit charged particles. If the sheets were exposed to these materials, they'd end up being discharged at a faster rate.
Perhaps some stuff in the atmosphere or in the floor, in the walls, were emitting radioactivity, which is essentially charged particles. And this is what was provoking this slow leakage of charge from electrostatic objects.
The solution seemed obvious. If Earth's radioactive materials were the cause, then they just had to be separated from them. In 1911, Theodore Wolff climbed the Eiffel Tower with an improved version of the electroscopes, hoping that it wouldn't get discharged. But he got another surprise. The electroscope was discharged at a faster rate than expected. So the solution was not to get separate from possible Earth radiations. In fact, this made the problem worse. Whatever it was discharging, the electroscopes didn't come from the Earth. In 1912, an Austrian physicist made the final step. Victor Hess did one of those crazy things that characterize scientists.
And what he did was to put an electroscope in a balloon, went up. It was quite a feat, because he went up to something like 5,000 meters. Going a balloon to 5,000 meters at that time, sitting in a little basket, it's probably a little bit frightening. But, science is a little bit like that. There is always a sort of adventure associated to that.
The measures that Hess took during the rise surprised everyone.
The highest he went, the stronger it went. So it meant that whatever effect was causing that, it got even stronger as he went up more far away from the ground.
The origin of that radiation was not to be found on Earth. If they wanted to understand where those particles came from, they had to look up into the sky. Cosmic ray astronomy was born. Almost 100 years later, we are at the Pierre Auger Astronomical Observatory. But this place is very different. None of the world's biggest telescopes can observe cosmic rays, but from here, we can. Pavel, one of our scientists at the Auger Observatory, tells us why this observatory is so different.
If you want to know what is out there in the skies, you start with what you can see with your own eyes. You investigate the visible light. In the past century, we built big telescopes to investigate also the radio portion of the electromagnetic radiation, and satellites, which investigate the ultraviolet part. But if you focus only on the electromagnetic radiation, you're missing on a big part of information which is actually coming to us from the space.
To study cosmic rays, we don't analyze the light coming from space. The principle is very different. We look for particles. These particles are mostly protons, about 90% of them. From the remaining 10%, most of them are helium nuclei. And we have 1% of electrons and heavier nuclei, such as iron or nitrogen.
Based on their energy, we can roughly categorize the cosmic rays into three main categories. We have the low-energy cosmic rays, which are coming from the sun, mostly because it's so close. Then we have the middle range of energies, where are cosmic rays coming from within our galaxy. And there is a good evidence that these cosmic rays are coming from supernovae, which are these massive explosions of stars. Finally, in the very, very highest energies, we believe the cosmic rays are coming from outside our galaxy. And there is a theory that actually they are coming from what we call active galactic nuclei, which are centers of the galaxies with very high star formation rate.
This is why the Pierre Auger Observatory is so different. Common telescopes in astronomy work with the light coming from space. But cosmic rays are particles, not light. They are tiny pieces of atoms that were thrown into space from different parts of the universe. Some extremely violent, such as black holes. Others nearby, like our sun. The low-energy cosmic rays coming from the sun produce one of the most beautiful phenomena on Earth.
What happens to these cosmic rays depends on how much energy they carry. If you have these low-energy cosmic rays, for example those which come from the sun, they are mostly shielded by the magnetic field of the Earth. So they follow the field lines of the magnetic fields and end up in the north and south pole regions, where you can see them as the magnificent northern lights. But there is also this other kind of cosmic rays, those very high-energy cosmic rays, which just go through the magnetic field and doesn't care about it at all.
If Aurora Borealis is a natural spectacle, the phenomenon that produces the highest energy cosmic rays is nothing less. But it has a peculiarity. Unfortunately, it's invisible to our eyes.
So these get into the atmosphere and hit a molecule of air. And on the interaction, it creates more particles, which are going in random direction. It's like a train collision. So before, all the cars of the train are going in a single direction. And after a collision, each car goes in a slightly different direction. So you take these particles from the interaction of the primary cosmic ray, and these particles hit other air molecules. So you have more particles and more interactions, and eventually you have this cascade of particles, trillions of them, which are going through the sky.
Thus, the difference between aurora borealis and these particle showers is the energy of the cosmic ray coming from space. The particles coming from the sun have little energy, and Earth's magnetic field deflects them towards planets' poles. There, in the upper ionosphere layers, they excite oxygen, nitrogen, and helium. When these gases return to their normal state, they emit photons, which is the light we're used to seeing in the northern lights. But Earth's magnetic field can't deviate from the most energetic particles. Cosmic rays coming from other stars reach our atmosphere at any point of the planet. There, they create a spectacular shower of millions and millions of new particles. A creation and annihilation of particles almost at the speed of light.
Most of them are absorbed by the atmosphere. Some of them, actually billions of them, reach the ground. So what you can do, you can just put the palm of your hand, and each second there are a couple of particles going through it. And these are the particles we can collect with the surface detectors.
1,660 tanks like this compose the Pierre Auger surface detector, all filled with water.
This is a model of what we call the surface detector. This is the main detector. We have 1,660 of them spread all over the field.
They are arranged in an area of 50 by 60 kilometers. This is the largest observatory ever built.
An area which is much larger than the largest city in the world.
When cosmic rays reach the surface, they are hunted by the water tanks. The information they provide is later analyzed by the scientists. A single cosmic ray can generate particle showers that spread across several square kilometers, so different water tanks can detect the shower at the same time.
But it's not the only way how we can figure out that the showers are actually there. When the particles go through the atmosphere, they excite the air molecules. So you have this energy stored in the air molecule, which is later shown as a light. So if your eye was more sensitive, you could see a flash of light going through the sky, and another flash, another flash. Because our eyes are not sensitive enough, we need to use so-called fluorescence detectors, which take a movie of the sky, very, very fast movie of the sky.
Ron Shellard shows us one of the fluorescence detectors. There are 4 buildings like this in the observatory. Inside, and only by night, these instruments hunt a faint light left by cosmic rays.
Okay, we just arrived here at the fluorescent detector. Actually, it's called Los Leones. If you look at this big map, we are exactly at this point here. We have 3 other. One is Coyeco, which is on this part of the map, on the west of the area. The other one is called Los Morados, which is here on the east side of the site. And then you have Loma Amarilla, which is way out quite in the north. And this part you have all the 1,660 tanks, which makes the surface detector of the Auger Observatory.
Behind these windows, several mirrors focus light on these highly sensitive electronic eyes. they can see a small light bulb more than 30 kilometers away. The 4 fluorescence buildings watch the sky over the water tank's grid. Thus, particle showers can be studied with 2 detectors simultaneously, the surface and the fluorescence ones, reaching an extreme accuracy. That's how the world's largest cosmic ray observatory works. It pursues the clues left in the atmosphere by the most energetic particles in the universe. The astroparticle study is a very young science. It has shown us that space is flooded with cosmic rays of very different natures and energies, but also that all beings on the planet live under a constant rain of particles that were born in distant stars. We are made of star stuff, but those stars keep flooding us every second with energetic particles. Can these particles somehow affect life on Earth? Could cosmic rays be a clear link between life and the most distant stars? To search for answers, we continue our journey. To understand the deep connection between cosmic rays and life, we stop at the Astrobiology Center facilities, an associated center with the NASA Astrobiology Institute near Madrid in Spain. And here, cosmic rays will give us a major surprise. Guillermo uses this vacuum chamber to simulate the space conditions and understand how the basic blocks of life can be created. Despite his hands being here, his mind travels every day to really distant places. Places such as gas and dust clouds between stars. These clouds are huge stains in the space formed mostly by hydrogen. There are also tiny pieces of dust made of carbon and silicates.
Inside dense molecular clouds, we have hydrogen and dust. The dust is covered with an ice mantle, mainly made of water, but also of other molecules such as carbon monoxide, carbon dioxide, or ammonia.
The gas and dust accumulation prevents radiation from nearby stars from going inside the cloud. But there are some space inhabitants that can easily reach the deepest and coldest areas.
Cosmic rays are the only radiation type that can permeate into a dense or dark molecular cloud.
The cosmic rays' energy is so high that it allows them to enter into the dark and cold dense cloud's interior. It is in this place, absolutely prohibited for life, where something unexpected happens.
In that extreme environment of low temperatures, close to absolute zero, is where we have found precursor life molecules, thanks to the best radio telescopes. Among them, there are some molecules that we believe are behind the formation of amino acids and molecules related to sugars.
Cosmic rays' energy discharges over molecules and the dust-frozen surface. This creates a very rich chemistry able to synthesize the first blocks to create life.
The presence of these prebiotic molecules in space wouldn't be so relevant if there weren't a way to transport them into a habitable zone.
The cosmic rays cook complex molecules inside dense clouds. But how can these molecules reach a planet? Inside dense clouds, stars and planets get born. During the formation, the temperature is so high that none of the interesting molecules for life could survive, although there's a place where they can hide and stay for a long time.
The microscopic dust particles agglomeration in our solar nebula eventually led with time to asteroid and comet formation.
These small bodies can stay away from high-temperature areas, keeping some of the molecules inside of them safe.
Radiation plays a dual role. From simple molecules, such as water, ammonia, or carbon monoxide, it shapes more complex molecules. But it also has a destructive role. By having a large body similar to an asteroid or comet, only the surface is exposed to radiation, so these complex molecules have been preserved inside.
Millions of asteroids fall over already formed planets with more stable conditions. Many of them carry seeds for life within them.
In meteorites, which would be a piece of asteroid fallen to Earth, up to 100 different amino acids have been found, which represents a significant number compared to the 20 biological amino acids that make up all living things.
But science needs proof, so a space mission like no other before was created.
The Rosetta mission from the European Space Agency has been a turning point in our knowledge about comets.
After an incredible 10-year journey, Rosetta intercepted one of the comets in our solar system.
After the first grounding, which was almost at the selected point in the comet, the probe bounced and did another 2 touchdowns. But we had a stroke of luck after the first landing when a dust cloud rose, and part of this dust came inside one of the instrument's tubes, the COSAC instrument.
The dust analysis that accidentally entered into the measuring instrument of Guillermo's team detected 16 organic molecules, some of them basic for life origin.
This is a universal phenomenon. Just as our solar system exists, we have discovered more than 1,000 extrasolar planets, many of them very similar to Earth. So as we receive this contribution from comets and asteroids, other planets similar to Earth could also receive them. Therefore, the starting point would be similar, and that would indicate that life is a phenomenon on a cosmic scale.
Far from Earth, among the stars, cosmic rays create essential molecules for life. But what about the cosmic rays that reach our atmosphere? Can they have any noticeable effect on life on the planet? To reveal how cosmic rays affect our atmosphere, we travel to Switzerland. Here, we meet Jasper Kirkby.
The atmosphere is crucial for life on Earth. It holds the temperature about 30 degrees warmer than if there was no atmosphere at all. That's the greenhouse gases, carbon dioxide and water. It also provides, of course, the oxygen that we breathe and the carbon dioxide that drives photosynthesis together with the sun.
The evaporated water from seas also travels through the atmosphere up to the mainland. This is where water's life cycle.
When you look at the Earth's atmosphere from space, from the space station, you see this thin blue line on the curve of the Earth. And it's a humbling experience when you realize how important that is for us to continue on Earth and how tenuous it is. It's just held down by gravity. What if it were to just disappear in a flash?
Our planet's history is full of mass extinctions, but all these extinctions had something in common. The atmosphere lost its ability to sustain life. The gases and dust released by meteor impacts or massive volcanic eruptions turned the atmosphere inhabitable.
So it's clear that the atmosphere is crucial for our life, but there's something that's behind the atmosphere that's driving it, that's causing all the processes that are important. So the sun drives processes in the atmosphere by light energy. The sun's light comes in, falls on the land or falls on the oceans and warms them up. So it warms up the land surface, and that warms up the air above it and circulates the air and transports energy and vapors from the Earth throughout the atmosphere.
For years, scientists have been finding matches between changes of solar activity and variations of Earth's climate.
So the sun is the main driver of the processes in the atmosphere. But what's interesting and what's not well understood at the moment, and is a very new line of thought, is that the distant stars, the cousins of our sun, are also, it looks like, responsible for some very important processes in the atmosphere.
And this is Jasper's research line, a new and exciting experiment to discover how distant stars affect our atmosphere. The CERN is located in the French-Swiss border. This is the home of well-known experiments such as the Large Hadron Collider, or LHC. But here, other experiments are developed as well, such as CLOUD.
So here we are in an experimental hall at CERN, next to the CERN proton synchrotron, which is behind a concrete wall over there, which is a low-energy accelerator, but every single proton that goes to the LHC goes through that accelerator, so it's actually one of the most important at CERN.
Under these concrete blocks, there are magnets that guide the protons to the cloud chamber. Inside this chamber, scientists simulate the composition and conditions for different atmospheres. So, this experiment allows us to see how the atmosphere behaves to the presence of ionizing particles.
Now, what you see in that silver cylinder down there is actually the thermal housing that surrounds the cloud chamber. The chamber itself, this 3-meter chamber, is inside of that, and it's a very special chamber because it's the cleanest chamber in the world. And in fact, it's the only chamber where we can do these experiments.
The chamber must remain perfectly clean inside so that the experiments can be performed with selected gas mixtures and without even minute amounts of contaminants.
Now, the importance of the particle beam is that it provides an adjustable source of cosmic rays. If you were to do these experiments in the atmosphere, you would have no control over the cosmic rays that are passing through.
It's impossible to access inside the chamber due to the need to maintain extreme cleanliness. But we can see underneath the chamber. From here, gases are added to recreate different types of atmospheres.
What you see here are a lot of valves where the gases for the cloud chamber enter the chamber itself. There are a number of different gases here: sulfur dioxide, ammonia, amines, biogenic vapors. Each of these has been identified as being precursor vapors that may lead to the formation of aerosol particles in the atmosphere, which can then grow to become the seeds for cloud droplets.
But why are the protons from the particle's accelerator reaching the mixture of gases?
It happens that if a cosmic ray goes through, it leaves a trail of ionization, and those ions help facilitate the formation of the embryonic seeds. They help stabilize these little particles. And so cosmic rays may have an effect on the formation of embryonic seeds, which then grow to become full-size seeds for cloud droplets.
This is a great finding. If cosmic rays are important for clouds formation, then they are also important for life on Earth. Clouds play a major role in shaping the long-term climate evolution of planets. This is a clear and direct way of linking cosmic rays with the conditions for life development. But we still need some more time.
We're investigating that now in cloud, and we don't have all the answers. We've seen that it does happen under certain circumstances, but we're by no means ready. We're not finished. And that's why we're doing the experiment. We still have many questions to answer.
It's too soon to say how important cosmic rays are for cloud formation. A lot of work still needs to be done. But Jasper had more to tell. There is another climactic phenomenon that is definitely linked to cosmic rays. A phenomenon that may be key to the development of complex molecules in primitive planets. A precious source of energy to form the first molecules of life.
This is connected with something called the global electrical circuit. About 100 kilometers above the Earth is the ionosphere. Cosmic rays flood rain through the atmosphere, and this causes a weak current to flow from the ionosphere down to ground, and it's purely allowed by cosmic rays.
Cosmic rays passing through our atmosphere open an electrical path in the air, which is crucial for lightning discharge.
And the really important role is played, or a really important role, by cosmic rays, because without cosmic rays, there would be much less lightning activity. So cosmic rays are very tightly connected with the global electrical circuit.
The relationship between electrical discharges in the atmosphere and life origin has been studied since the 50s with incredible results. The energy of lightning in primordial atmospheres allows the creation of complex molecules, like amino acids, from simple gases as ammonia, methane, and water. So cosmic rays, and the lightning they cause, may be responsible for creating the primordial soup of molecules that gave rise to life on our planet. We have found another way in which cosmic rays can shape and create life in the universe. But before continuing, we have time for one last coffee with Jasper.
Stars are the forges that made the atoms that we're made of, and our local star, the Sun, has provided this Goldilocks environment that has allowed us to live, has allowed water to exist on Earth, and has allowed life to flourish and people to develop. But we've learned that the stars may not have abandoned us with just making our atoms. They may have continued to look over us through cosmic rays. Out there in the Milky Way, there's a supernova exploding every 50 years or so. And this is bathing the Milky Way and our Earth with cosmic rays. And these cosmic rays have been affecting life as well, continuously, since the beginning of the Earth. They've been affecting the formation of lightning, affecting almost certainly the formation of aerosol particle seeds for clouds, and also causing a steady mutation of DNA that, once life had started, allowed the complexity of life and human beings to develop.
These words from Jasper led us to the final stop of our journey. Here we will discover another disturbing link that binds us to cosmic rays, a union point between the most violent phenomena in the universe and the genetic information that travels inside each of our cells. To help us understand this deep connection, we find Eduardo, a researcher at the Center of Astrobiology in Madrid.
Life on our planet was originated about 3,800 million years ago. During all this time, the Earth has undergone many changes that have affected the composition of gases in the atmosphere and oceans. It has also affected temperatures. There have been many variations in temperatures. And also the natural radiation levels have been affected. Despite all of this, life has been successful. Life has won and has managed to spread to virtually every corner of our planet.
But all this incredible diversity of living things have something in common, something within each cell, even in the simplest organisms, a molecule which allows the transmission from one generation to another of the information needed to create new individuals.
Inside each of the cells of this plant, there are molecules known as the DNA. These DNA molecules are used to store all genetic information, used to build a particular organism. In this case, these DNA molecules serve to generate a plant of the species Monstera deliciosa.
However, those copies, the molecular replication that is passed from one organism to the next generation, are not identical. During the process, some errors occur. Changes in the molecular structure known as mutations. They are minor changes, almost imperceptible, but these changes have allowed the vast diversity of life as we know it.
The mechanisms that are involved in DNA copying are not perfect and often introduce errors during the copy process. And then there are also external agents that are responsible to change or modify the sequence of the DNA molecule. Among these external agents are some toxic chemicals or radiation.
All living beings are exposed to natural radiation levels. Rocks and minerals contain small traces of potassium, uranium, thorium, and other radioactive elements. But it is not the only natural source of radiation to which we are exposed that can alter our genetic code.
In the past, our planet may have been affected by much higher doses of cosmic radiation, possibly because of the explosion of a nearby supernova or some other events that happened in the sun. Cosmic radiation that occurred in the past possibly performed a very important role, increasing mutations in living organisms of that time, and somehow accelerated the evolutionary process. We cannot rule out that the current cosmic radiation that exists today, even at lower doses, could also have some effect on the rate of mutation of living organisms. Obviously, there is a clear link between what happens in the stars and how life has been modeled on our planet, or even elsewhere where there may be similar life forms.
So far, scientific studies have not been conducted to show the level of importance the cosmic radiation has on the evolution of living beings. Only now we have the tools to do so.
It has some complexity. We need to study many generations of individuals to see the mutation rate in conditions in which there is a total absence of cosmic radiation, and then compare it to normal conditions with the cosmic radiation dose that exists on Earth right now.
This is a new and exciting research field that promises disturbing results for the coming years. Modern techniques of DNA sequencing and the relentless advance in the knowledge of cosmic radiation are the tools that new researchers need to demonstrate the deep bond between the stars and life in the universe. Here ends our journey. Following the trail of the most energetic particles in the universe, we have found that inside cold molecular clouds, or in the atmosphere of our planet, or even in the depths of our molecular structure as living beings, cosmic rays bind us with the most violent and beautiful processes occurring in the universe. The stars produce the atoms from which we are made, but they did not stop there. Every time a star dies, it floods the space with energy particles traveling for millions of years, arousing the spark of life anywhere in the universe.